Imagine shrinking our entire solar system until the sun itself is no larger than a glowing bead in your hand. Around it, the planets fall into place, tiny specks circling at invisible distances. At this scale, Earth would be smaller than a grain of dust orbiting just a few steps away. But the nearest star, you would need to travel thousands of kilometers before encountering it. This is the true nature of our cosmic neighborhood. Vast stretches of emptiness separating islands of light. The distances are so immense that even the fastest spacecraft humanity has ever built would take tens of thousands of years to cross the gulf to the nearest star Proxima Centauri. And yet even that star is practically next door in the scale of the galaxy. Our solar system itself is already vast beyond comprehension. Light from the sun, travelling at 300,000 kilometers per second, takes just over 8 minutes to reach Earth. But it needs more than 4 hours to reach Neptune, the outermost planet, and over half a day to cross the boundary where the sun's influence fades into interstellar space. Beyond that, in the dark, drifts the Oort cloud, a hypothetical sphere of icy bodies that may extend nearly 1 light-year from the sun. Even here we are still within our local neighbourhood. When astronomers first tried to grasp these distances, they resorted to metaphors. Imagine the sun shrunk to the size of a basketball. On this scale, Earth would be a tiny grain of sand orbiting 30 meters away. Neptune would be more than 900 meters out, nearly a kilometer. And the nearest star, Proxima Centauri, would not be down the street. It would be thousands of kilometers away, far beyond the horizon. This is the first step in the ladder of cosmic perspective, realizing how small our solar system is compared to the gulf of space between stars. It is like discovering that the village you thought was the whole world is merely one house in an endless city. And yet even this city is only a tiny part of a much grander design. When we lift our gaze from stars to galaxies, the scale explodes. The Milky Way, our galactic home, contains more than 200 billion stars. It stretches 100,000 light-years across a disk of spiraling arms wrapped around a glowing core. To cross it from end to end, light itself, the fastest thing we know, would need 100 millennia. And yet to us it appears as nothing more than a faint band of light smeared across the night sky. We live not at the centre, but on the outskirts in a quiet spiral arm called the Orion Arm. From here the galaxy looks serene, but within its depth stars are born and die in spectacular fashion. Supernovae explode with the brilliance of entire galaxies. Black holes lurk in silence. Gas clouds stretch for hundreds of light-years nurseries where new stars ignite. The Milky Way is not static. It is alive, changing, evolving. This awareness that our solar system is a speck in a galaxy, and that our galaxy is only one among countless others, is the foundation of the journey ahead. Step by step, we will climb from the familiar into the unimaginable, from what we can measure with instruments to what we can barely conceive. And with each step, the universe will grow larger, stranger, and more awe-inspiring. If the Milky Way were the only galaxy in existence, it would already be overwhelming. But it is not alone. Just beyond our spiral home lies Andromeda, a majestic spiral galaxy more than 2 million light-years away. In the night sky it appears faint, barely visible to the naked eye as a smudge of light. Yet through a telescope its grandeur is revealed. A swirling disk larger than the Milky Way, glowing with 1 trillion stars. Andromeda is not just a neighbour, it is our future. Gravity is pulling our galaxies together, and in about 4 billion years they will collide. When that happens, their shapes will twist and distort. Stars will be flung into arcs and tails. Their central black holes will spiral inward, eventually merging. Out of this cosmic encounter will emerge a new galaxy, often nicknamed Milkomeda, a giant elliptical shining brighter than either of its parents. For now, though, Andromeda drifts serenely approaching us at hundreds of kilometers per second, the slow choreography of the cosmos. The Milky Way and Andromeda are the dominant members of what astronomers call the local group. This is a small collection of more than 50 galaxies bound together by gravity. Many of them are dwarfs, tiny irregular smudges containing only a few million stars. Others, like Triangulum, are graceful spirals in miniature. These galaxies orbit and interact like members of a family, exchanging gas and stars over billions of years. Seen from afar, the local group would appear as a small knot of galaxies adrift in the cosmic ocean. It spans about 10 million light-years across a vast distance compared to our solar system, yet only a tiny bubble compared to the universe at large. Within this group, galaxies tug at one another, merge and evolve. It is the first layer of cosmic structure beyond our own galaxy. the neighbourhood in which the Milky Way resides. What makes the local group remarkable is not its size, but its role as a stepping stone in perspective. To grasp its scale is to begin to understand how galaxies organise themselves. They do not scatter randomly. They gather, cluster, and weave into patterns dictated by gravity and dark matter. The local group is a microcosm of this universal principle. Astronomers often compare it to a small town. The Milky Way and Andromeda are like the two largest buildings towering above the rest. The smaller galaxies are like cottages scattered around. Some cling closely to the giants orbiting as satellites. Others drift further out, hovering at the edge of the town's reach. And beyond that edge lies emptiness until we step into the next level of cosmic structure. For now, the local group is our immediate home in the grand hierarchy. It reminds us that galaxies are not isolated islands. They are members of communities shaped by their neighbours as much as by their own internal processes. And just as towns belong to counties and counties to nations, the local group is part of something far larger. The journey outward has only begun. Beyond our group of galaxies, the structures grow more immense, more intricate, and more mysterious. The next step will take us to clusters, cosmic cities where hundreds or even thousands of galaxies gather. The local group, for all its immensity, is just a small town compared to the great cities of the cosmos. Galaxy clusters. The nearest of these to us is the Virgo cluster, lying about 60 million light-years away. Through a telescope, Virgo does not appear as a single object, but as a swarm over 1,000 galaxies bound together by gravity, moving in a slow but intricate dance. To appreciate the scale, imagine the Milky Way drifting within this vast structure. Our galaxy, enormous by human standards, would look like a single street lamp within a sprawling metropolis. Elliptical giants hundreds of thousands of light-years across dominate Virgo. They contain trillions of stars and masses so large that they anchor the orbits of dozens of smaller galaxies. Around them whirl spirals, irregulars, and dwarfs, each playing a role in the cluster's gravitational symphony. What makes clusters extraordinary is not just the galaxies themselves, but the invisible matter that binds them. Observations show that the combined gravity of stars and gas cannot account for the motions within Virgo. Something unseen, something weighing far more than all the visible matter holds the cluster together. This is the clearest sign of dark matter, the mysterious substance that makes up most of the universe's mass. Without it, the galaxies of Virgo would simply fly apart. Clusters also glow in ways invisible to the eye. Between the galaxies lies hot gas heated to millions of degrees. This gas emits X-rays detectable by specialized observatories. It fills the cluster like a fog, and its mass outweighs that of all the stars combined. Webb cannot see this radiation, but paired with other telescopes, it paints a picture of clusters as ecosystems, complex environments where galaxies grow, merge, and transform. Virgo is not an isolated city. It is part of an even larger arrangement, the Virgo supercluster, a sprawling collection of clusters and groups stretching over 100 million light-years. Our local group lies on the outskirts, a satellite suburb of this grand structure. To map Virgo is to see the first hints of the cosmic web, filaments of galaxies linking one cluster to another, threads of matter stretching across the void. To think of these scales is to realize that galaxies once thought to be ultimate islands of the cosmos are themselves citizens of larger nations. They gather in associations, trade matter, collide, and reshape one another. Clusters are the building blocks of the universe on its larger scales, and yet even the Virgo cluster with its 1,000 galaxies is still only a piece of something greater. Step beyond, and we begin to trace superclusters, interconnected regions of space so large that light itself takes hundreds of millions of years to cross them. These are the continents of the universe, the landscapes upon which all cosmic history is written. Beyond the Virgo cluster lies a landscape so vast that even galaxies seem small. Astronomers call it a supercluster, a continent of the cosmos stitched from many clusters and groups. Our home resides on the fringe of one of these giants, a domain whose Hawaiian name captures its spirit, Laniakea, meaning immense heaven. It spans hundreds of millions of light years, and its rivers of gravity guide entire families of galaxies, drawing them toward common basins like water flowing down a mountain range. To imagine Laniakea replace streets and cities with filaments and clusters, the Virgo cluster is one city among thousands. The local group with the Milky Way and Andromeda is a suburb riding a slow current. Every galaxy is a boat in that current carried not by wind but by the invisible pull of mass spread over unimaginable distances. Where the currents converge, clusters thicken. Where they diverge, voids open like blue water on a map. How do we know we belong to Laniakea? By measuring subtle motions. Galaxies are not simply receding with cosmic expansion, they also drift under local gravity. When astronomers map these flows, they find a grand basin of attraction far beyond Virgo, a region toward which many galaxies move together. Our home and its neighbours slide along the same slope of space-time, bound not by walls but by the geography of gravity. The borders of a supercluster are not fences but watersheds. Cross an invisible ridge and a galaxy would be pulled toward a different basin, a separate destiny. This way of seeing redraws the sky. What looks like scatter becomes topology. Space-time is contoured and galaxies ride those contours like leaves on slow rivers. Laniakea is not eternal. Over billions of years, its pieces will continue to merge while the greater universe thins as expansion accelerates. Yet the pattern matters now. It shows that structure in the universe is hierarchical. Stars within galaxies, galaxies within groups, groups within superclusters, all nested in a web whose scale defeats ordinary language. Stand back one step more and Laniakea itself becomes just one panel in a mosaic. Other superclusters lie beyond, some connected by tenuous bridges of galaxies, some separated by yawning voids. From this height of imagination, the Milky Way is a single spark riding a slow tide across an immense heaven, passing milestones we can name but never visit in a lifetime. There is humility in such cartography. We draw borders around Laniakea today because current data favour those watersheds. As measurements improve, the lines may shift, the basin may widen or narrow, tributaries may be reassigned. That is expected. The map is not the territory, it is a living draft that converges as evidence accumulates. What endures is the concept. Gravity carves the universe into drainage patterns on a scale so large that entire galaxies flow like raindrops. Peer a little farther and the currents meet still larger structures. The Shapley concentration looms like a continental shelf, its mass tugging on galaxies across hundreds of millions of light years. Flow lines bend toward it and our own path leans subtly in that direction. We do not sail alone. Entire flotillas of groups share our drift. The realization is strangely intimate. The fate of the Milky Way is written not only in its own mass and neighbours, but in the distant terrain of space-time. If superclusters are the continents of the universe, the cosmic web is the world itself, a lattice of matter stretching across space. Its filaments threaded with galaxies and its nodes ablaze with clusters. Between the strands yawn vast voids, regions almost empty where a single galaxy might wander for hundreds of millions of light years without meeting another. Computer simulations predicted this web decades ago. Modern surveys have traced it nearby. With deep infrared vision, we glimpse its younger form already sketched by gravity long before the present day. Why a web at all? In the early cosmos, tiny ripples in density grew under gravity. Dark matter abundant and slow to interact collapsed first, forming invisible scaffolds. Ordinary gas fell onto those scaffolds, heated and cooled, and eventually ignited as stars. Gravity pulled more matter along the same paths, amplifying the pattern, like water carving deeper channels into soft earth. The result was not a uniform soup, but a grand network of veins and arteries feeding galaxies with fresh gas and carrying away their waste. We do not see dark matter directly, but it leaves fingerprints. One is gravitational lensing. Mass bends light, distorting the shapes of background galaxies. Map the distortions across a field and you sketch the hidden mass. Another is motion. Galaxies within filaments stream toward nodes, while those inside clusters orbit in crowded swarms. The choreography betrays the invisible choreographer. The filaments are not mere bridges. They are lifelines. Galaxies starve without gas. Star formation fades and the lights go out. Along a filament, gas can flow inward for billions of years, replenishing the fuel for new stars. The densest junctions become bustling intersections, while isolated galaxies in the emptiest voids grow old and quiet like towns bypassed by every road. Voids matter too. They expand faster than crowded regions, stretching the web, sharpening contrast and giving cosmologists clean laboratories to test gravity. A single supernova in a lonely void galaxy writes a clear line in data unblurred by neighbours. In this way, emptiness becomes an instrument. From the right distance, the web resembles a fog of glass threads crisscrossing the universe. Up close, each thread is a chain of islands. Closer still, each island is a city of stars. Scale is the trick of the cosmos. The pattern endures while the pieces change. Learn the pattern, and the universe begins to make sense. New instruments push the web into view. Radio arrays map neutral hydrogen. X-ray telescopes reveal the hot atmospheres of clusters that sit at the web's nodes. Optical surveys trace billions of galaxies, drawing the bones of the structure in exquisite detail. Webb adds the earliest chapters, catching newborn galaxies already aligned along threads laid down by dark matter. The agreement between maps at different wavelengths and different eras is the victory of a theory tested from many angles. Because the web connects everything, small causes can have large effects. A stream of cold gas pouring down a filament can ignite a starburst that reshapes a galaxy's future. A merger at a node can quench star formation by heating the gas supply. Feedback from black holes can blow winds along the strands, changing the fate of neighbours downstream. The web is not background. It is the stage and the script. Even the emptiness instructs. Light travelling through a void suffers less gravitational tug arriving slightly earlier than if it had taken a denser route. By timing many signals with care and comparing paths, cosmologists test models of gravity itself. Some proposals for physics beyond the standard model would subtly alter how voids grow or how filaments thickened. The web thus becomes a laboratory for ideas as well as a map of matter. Stand at any scale you like and the motif persists. Branches into twigs, into leaves. The same mathematics that describes river deltas and lung bronchi appears in the spacing of galaxies. Nature reuses patterns when they are efficient. The universe did not need to be beautiful, but it often is. We once imagined a universe of isolated islands. The web replaces that picture with a circulation system. Gas flows in along filaments, forms stars, is blown out by winds, and supernova cools and flows in again. Over and over the cycle continues, moderated by environment. A galaxy at a junction will live a different life than one suspended in a quiet strand. The web turns statics into dynamics, geography into biography. To measure a universe this large, astronomers built a ladder of distances, each rung calibrated by the one below. At the ground level are trigonometric parallax measurements. As Earth moves around the Sun, nearby stars shift slightly against the distant background. That wobble, tiny yet precise, gives the first reliable steps out of our neighbourhood. Beyond parallax, a new rung appears. Standard candles, objects whose true brightness is known. If you know how bright a thing really is, you can compare it to how bright it looks and deduce the distance. Gefied variable stars serve as such candles. Their pulsation period tells their luminosity, a gift of physics that turns rhythm into a yardstick. By finding Cepheids in nearby galaxies, astronomers stretch the ladder across intergalactic space. Further out, supernovae of a particular type become the next rung. These explosions reach nearly uniform peak brightness, bright enough to be seen across billions of light years. Plot their distances against how fast those galaxies are receding, and you trace the history of cosmic expansion. This is how we learned that the universe is not just expanding, but accelerating a discovery that revealed the presence of dark energy. Each rung demands careful calibration. Dust can dim a candle. Chemistry can shift a star's rhythm. The ladder's strength lies in overlap. Methods cross-check one another, anchoring the scale with redundancy. Where the rungs disagree, tension arises, and those tensions often hint at new physics or hidden systematics. The debates about the precise rate of expansion, the so-called Hubble tension, grow from these meticulous comparisons. The ladder's not only about light. Sometimes gravity provides the yardstick. In rare alignments, a foreground galaxy lenses a background supernova or quasar into multiple images. Light from each image travels a different path length and crosses regions of different gravitational potential. Measure the time delays between the flickers and you can solve for distance and the geometry of space-time itself. In the end, the distance ladder is a story about turning change into measure. A star's pulse, a supernova's flare, a planet's orbit, a photon's delay. From these rhythms, we chart a cosmos too vast to survey with any single ruler, and the map holds together not by assumption, but by the harmony of many independent notes. No single rung suffices everywhere, so astronomers engineer overlap. Spacecraft triangulate parallaxes with baselines larger than Earth's orbit, sharpening the first step. Cepheid measurements are tied to galaxies that also host supernovae welding two rungs together. Nearby galaxies with water mazes provide geometric distances that check both. With each weld, uncertainty shrinks and the vast takes on edges we can trust. Yet puzzles remain. Independent routes to the expansion rate yield answers that differ by a few percent, small in number, large in meaning. Either subtle systematics hide in the data or new physics waits in the wings. Perhaps a change in dark energy's behaviour, an extra species of light particle in the early universe, or a calibration shift we have not yet noticed. The fact that careful measurements disagree is not a failure. It is where progress begins. Beyond candles and lenses, a different ruler spans the sky. Ripples from sound waves in the hot plasma of the early universe now frozen into the large-scale distribution of galaxies. These baryon acoustic oscillations provide a standard yard built into space-time itself. Measure their scale at different epochs, and you recover the expansion history in another key harmonizing with the rest of the ladder. Distances are the spine of cosmology. Without them, brightness misleads, size deceives, and motion cannot be interpreted. With them, scattered measurements lock together into a narrative. A Cepheid in one galaxy calibrates a supernova in the same galaxy, which calibrates galaxies 1,000 times farther away, which anchor models of the early universe that predict ripples we measure across the sky today. The ladder is not a gadget. It is the discipline of consistency made visible. The ladder reaches into the microwave background as well. Tiny ripples in that ancient light encode absolute scales set by physics in the first minutes. Combine those scales with today's maps, and you obtain yet another route to distance linking the youngest snapshot of the universe to the present in a single chain. When independent chains agree, confidence deepens. When they do not, the discord points to the next question we must ask. Calibrators have personalities. Cepheids are bright, but exist only in star-forming regions where dust is thick. Supernovae reach far, but are rare and unpredictable. Mesas give geometry, but require special conditions. Each method demands craft, and that craft is cumulative, passed from observer to observer like a well-worn tool. The romance of astronomy is often about first light. The reality is that precision comes from repetition and stubbornness. Once distances are known, motion comes into focus. A century ago, observers found that the light from most galaxies is shifted toward the red, stretched to longer wavelengths. The farther the galaxy, the greater the shift. This simple relation distance proportional to recession speed is the signature of expansion. Space itself is growing, carrying galaxies apart like dots on an inflating balloon. Expansion does not mean galaxies are flying through space away from a center. There is no center. Every observer, wherever situated, sees distant galaxies receding. It is geometry, not a blast. The scale factor of the universe increases with time and wavelengths. Stretch with it. So even ancient photons arrive with their colors changed. A fossil record of the journey. For nearby galaxies, we can treat redshift as a speed. For distant ones, the picture is subtler. General relativity frames the change not as motion through space, but as growth of space. Equations translate redshift into look-back time, comoving distance, and the history of expansion. These are the tools that let us say how old the light is, how far the source is now, and how the universe has changed between emission and arrival. The relation between distance and recession is governed by the contents of the universe. Matter slows expansion, dark energy speeds it up. Radiation mattered long ago. By fitting models to the observed pattern, a curve, not a line over great distances, we infer the proportions of matter and dark energy. That is how we learned that ordinary matter is only a small share of the cosmic budget, while dark matter and dark energy dominate the ledger. On small scales, gravity can resist expansion. Galaxies remain bound. Clusters hold together. Local flows add peculiar velocities to the general recession. Little swirls superimposed on the grand current. But at sufficiently large scales, the expansion wins and the simple, graceful relation reappears. What began as a red tint in a spectrograph becomes a narrative about the whole universe, its age, its ingredients, and its fate. From a stretched wavelength, we recover a history of growth written across billions of years. Expansion also stretches time. A supernova in a very distant galaxy rises and fades more slowly when seen from here, because the clock of the emitting galaxy is dilated by the same factor that stretches its light. This prediction is not optional, it is baked into the geometry. Observers have watched the effect directly. a clean confirmation that the redshift is not a mere quirk of tired light, but the imprint of expanding space. The picture has practical consequences. If expansion continues to accelerate, distant galaxies will slip beyond our event horizon. Future astronomers living in a very far epoch would see only the remnants of the local group marooned in an ever darker sea. The evidence for the Big Bang would become harder to read. We live in a privileged moment when the sky still contains the clues to its own beginning. None of this requires mysticism, only patience. Spectra gathered one by one add up to a curve that speaks of matter and dark energy. Distances measured by many methods agree within small margins and then disagree just enough to be interesting. We refine instruments, repeat observations, and watch the numbers either converge or insist on telling us something new. In this way, a few lines in a spectrum become a window on the grandest questions we can ask. Make a mental picture. Paint galaxies as dots on the surface of a balloon and draw a tiny bug between two dots. As the balloon inflates, the bug sees every dot move away and the farther dots move faster. There is no center on the surface yet, expansion is everywhere. The analogy is imperfect but helpful. It rescues intuition from the trap of imagining an explosion into empty space. Space itself is the thing that grows. The same mathematics that relates redshift to distance also predicts how structures grow. Measure how clumpy the galaxy distribution becomes with time and you test gravity itself. If observations ever drift away from expectations, it could mean that dark energy changes with epoch, or that general relativity needs modification on cosmic scales. Thus a spectrum from a single galaxy joined to many others becomes a referendum on the deepest laws we know. In classrooms, the first lesson is the line on a plot. In observatories, the last lesson is that the line bends and the bend contains the story. Our task is to trace that curve with relentless care, linking a humble redshift to the architecture and fate of everything we can see. Here is a paradox that startles newcomers. The observable universe has a radius of about 46 billion light-years, yet the age of the universe is about 13.8 billion years. How can we see farther in light-years than the number of years that light has had to travel? The answer lies in expansion. When a photon left a distant galaxy billions of years ago, the space between us was smaller. As the photon crossed the void itself grew. The light kept moving, but the destination receded. By the time the photon reached us, the original source had been carried far away by cosmic expansion. The distance the light travelled the path length along the journey is not the same as the current separation between us and the source. Cosmologists use several distance measures to keep this straight. Look-back time tells how long the light has been travelling. Proper distance describes how far the source is from us now at this moment in cosmic time. Comoving distance factors out the expansion, so that coordinates expand with the universe freezing structure onto a grid that stretches uniformly. The headline number, 46 billion light-years, refers to the current proper distance to the farthest light we can observe. There is also a horizon we cannot cross. Beyond a certain redshift, light emitted today will never reach us because expansion accelerates, pushing space apart faster than light can bridge new gap. This is the cosmic event horizon, a boundary not of matter but of causality. It limits what can ever be known by observers like us, even with perfect instruments and infinite patience. Far from shrinking the universe, this realization makes it larger in our minds. This sphere we can see is only the part that has had time to send us light. Beyond that sphere, the universe likely continues, perhaps indefinitely. Our maps end not at an edge of matter, but at an edge of time. So when we say the observable universe has a certain size, we are describing a moving target, a bubble that grows as more ancient light arrives, even while distant regions slip forever out of reach. It is a strange geometry, but it is the geometry that the data demand. Think of the observable universe as a growing archive. Each day, new pages arrive from slightly more distant sources, even as the shelves holding the furthest future volumes recede out of reach. Our instruments read the pages in reverse order. The youngest nearby first, the oldest farthest last. Webb specializes in the oldest legible pages, long faded to infrared ink, still decipherable with gold mirrors and cold eyes. This view does not make us insignificant. It makes us participants. By measuring horizons and distances with care, we turn a bewildering geometry into a comprehensible atlas. The paradox dissolves, replaced by a rule. In a changing universe, distance means many things, and clarity begins by naming which one we are using. Behind the terms and horizons sits a simple message. The universe is dynamic and language must keep up. Words like near and far, then and now, here and there need qualifiers when space-time itself evolves. Once that habit forms the puzzle of 46 billion light-years beside 13.8 billion years, becomes not a contradiction but a lesson in how to speak about a changing stage. One last image. Imagine a swimmer caught in a slow current moving away from shore. The swimmer strokes steadily toward a lighthouse. Each stroke brings progress, yet the shoreline slides backward. After hours, the swimmer reaches the beacon exhausted and looks back to see the starting point now far behind. Light is that swimmer. Space is the current. The destination is our telescope. The map must record both the path taken and where the shores now lie. With that, the headline figures become anchors rather than riddles. 46 billion light-years names the present reach of sight. 13.8 billion years names the time since the first light could travel freely. Between them stretches a living universe where distance and time are partners, in a dance we have finally learned to describe. And this is why every deep field feels like a message from far away. Each pixel carries both a distance travelled and a distance remaining a past recorded and a present revealed. Name them carefully and the paradoxes turn into coordinates on a map that grows clearer with every observation. The most ancient light we can observe does not come from stars or galaxies. It comes from the universe itself, from an era before the first stars ignited. About 380,000 years after the Big Bang, the hot plasma of the young cosmos cooled enough for electrons to combine with protons forming neutral hydrogen. Suddenly the fog lifted. Photons once trapped in endless scattering streamed freely into space. We still see that radiation today as the cosmic microwave background. To the eye, it would be invisible microwaves are far beyond our vision, but with radio telescopes and satellites we can map it across the sky. The result is astonishing. A nearly uniform glow, the same in every direction to 1 part in 100,000. Yet in those faint ripples lie the seeds of everything. Slightly denser patches became galaxies and clusters. Slightly thinner patches became the voids. The map of the microwave background is nothing less than the blueprint of the cosmic web. The temperature of this background is just under 3 degrees above absolute zero, but its tiny variations encode a wealth of information. By analysing them, astronomers infer the age of the universe, its composition of matter and radiation, and the balance of ordinary matter, dark matter, and dark energy. These ripples are fossils of sound waves that once rolled through the primordial plasma, and their pattern still marks the large-scale structure today. The cosmic microwave background is often called the afterglow of creation, but it is more like the first clear photograph. Everything before it is hidden behind the fog of plasma. Everything after it is history unfolding. To measure it is to measure the foundation. Satellites like COBE-WMAP and Planck refined this map to exquisite precision. Each mission confirmed the broad picture. A universe about 13.8 billion years old, expanding, filled mostly with dark matter and dark energy. The agreement across instruments and techniques is one of the triumphs of modern science, yet mysteries remain. The largest scales of the background show anomalies, a cold spot larger than expected alignments that seem to defy randomness. Whether these are statistical flukes or hints of new physics is debated still. Webb does not observe the microwave background directly, but by studying the first galaxies it connects the blueprint to the finished structure testing. Whether the early seeds grew as predicted. Long before the microwave background formed, another process set the stage: cosmic inflation. According to theory, in the first fraction of a second, the universe expanded faster than even light could cross it. Distances grew by unimaginable factors in an instant, stretching quantum fluctuations to cosmic scales. Inflation explains why the microwave background looks so uniform. Regions that appear far apart were once close enough to share conditions before being pulled beyond one another's horizons. It also explains why the universe is flat to high precision, as inflation smoothed any curvature. Most importantly, it provided the initial seeds of structure. The tiny quantum jitters inflated into density variations that gravity would later amplify into galaxies and clusters. Detecting direct evidence of inflation is difficult. One signal would be primordial. Gravitational waves, faint ripples in space-time that could leave a subtle imprint on the polarization of the microwave background. Experiments have searched for this fingerprint, and though hints have appeared, conclusive proof remains elusive. If found, it would be a window into physics at energies beyond any collider. Inflation may have been brief, but its consequences are eternal. It determined the size of the observable universe, the pattern of ripples in the microwave background, and the scaffolding of the cosmic web. Competing models exist. Some suggest inflation was driven by a field that later decayed. Others propose more exotic scenarios, including eternal inflation, in which our universe is only one bubble among countless others. For now, the simplest models fit the data remarkably well. The spectrum of fluctuations in the microwave background matches predictions. The large-scale structure aligns with expectations. The cosmic web itself, traced by billions of galaxies, follows the contours drawn by inflation's brush. The elegance of the theory is that it links the smallest scales of quantum physics to the largest scales of cosmology. If future observations confirm inflation's fingerprints, we will have touched the very first moment when the universe acquired its character. We will have glimpsed the engine that turned uncertainty into structure and silence, into the music of space and time. From quantum jitters to galaxies is a long road, but gravity does not waste time. Over billions of years, those ripples grew into the vast structures we see today. The process is called structure formation, and it is the story of the universe turning smoothness into complexity. In the early universe, dark matter dominated. Unlike ordinary matter, it did not interact with light or radiation, so it began clumping earlier. These clumps acted as gravitational wells. Ordinary gas fell into them, cooled, and eventually formed stars. The first galaxies were born in the densest pockets, while emptier regions became the vast voids. Simulations have traced this growth with striking detail. Starting from the ripples seen in the microwave background, computers evolved billions of particles under gravity. The result is a cosmic web of filaments and clusters, nearly indistinguishable from real surveys. Galaxies string along filaments like pearls on a necklace, and clusters glow at the intersections. Webb and other telescopes confirm this picture by observing galaxies at different epochs. The youngest galaxies appear small, irregular, and blue with intense star formation. Later galaxies grow larger, redder, and more ordered, shaped by mergers and feedback. By stitching these snapshots together, astronomers reconstruct a time-lapse of structure formation, spanning 13 billion years. Feedback is crucial. Exploding supernovae and voracious black holes pump energy back into their surroundings, heating gas, blowing winds, and regulating star formation. Without feedback, simulations produce too many stars too quickly. With it, galaxies evolve into forms we recognize. Spirals with steady disks, ellipticals with quenched cores, dwarves struggling against the tides of their neighbors. Structure formation is both predictable and stochastic. On large scales, the web always appears. On small scales, details vary. Which galaxy collides with which when stars ignite, how feedback sculpts the result. This blend of law and chance mirrors evolution in biology. The pattern is robust, but the specifics are unique. Every cluster and filament we see today is the matured form of those early ripples. Each galaxy carries the imprint of its ancestry. To read them is to read the fossil record of gravity's patient work written across billions of light years. Stars are the visible punctuation marks of structure formation. They turn gas into light chemistry and eventually life, but their history is not uniform. The universe has passed through distinct eras of star formation, each leaving its mark on the galaxies we see. The first stars, known as Population 3, were Titans. Formed from pristine hydrogen and helium, they lacked the cooling agents provided by heavier elements. As a result, they grew enormous, hundreds of times the Sun's mass, and lived only a few million years before exploding. In their deaths, they forged the first carbon, oxygen, and iron, enriching their surroundings for the next generations. Later stars, Population 2, were smaller and longer lived. They carried traces of those early metals, enough to allow more efficient cooling and more moderate masses. Many ancient globular clusters still host these stars today. Fossils from the early universe orbiting the Milky Way. Finally came Population 1 stars like our Sun, rich in metals and capable of supporting planetary systems. These stars dominate the modern universe. Their diversity in size, age, and chemistry reflects billions of years of recycling, mergers, and evolution. The history of star formation peaks about 10 billion years ago, a time astronomers call cosmic noon. Galaxies then were ablaze, converting gas into stars at furious rates. Since that peak star formation has declined as gas supplies dwindled and feedback heated what remained, our era is quieter with galaxies forming stars at a more modest pace. Webb has pushed observations into the epoch when the first stars ignited. It detects galaxies less than a few 100 million years old glowing faintly but clearly. Their light stretched into infrared carries the signatures of those early populations. By comparing spectra, astronomers can identify chemical fingerprints and track the enrichment of the cosmos. The sequence is clear. Massive first stars enrich, moderate later stars stabilize, and abundant present stars diversify. Together they build the chemical table of the universe element by element. Without them, planets and biology could never arise. The arc from simplicity to complexity is traced in every atom heavier than helium. The growth of structure and the rise of stars are shaped not only by matter, but also by something stranger: dark energy. Its discovery came from a simple question: how fast is the universe expanding? The answer shocked us. By the late 20th century, astronomers had measured the expansion rate using supernovae as standard candles. They expected to see the rate slowing as gravity from matter tugged on galaxies. Instead, they found the opposite. Distant supernovae were dimmer than predicted, meaning they were farther away. The expansion was not decelerating, it was accelerating. Some unknown energy was pushing space apart. Dark energy, as it was named, dominates today's cosmos. About 70% of the energy content of the universe lies in this form. Its nature is a mystery. It could be a property of space-time itself, a cosmological constant that Einstein once introduced and later abandoned. Or it could be a dynamic field that changes with time. The evidence is robust. The microwave background galaxy surveys and supernovae all point to the same conclusion. Acceleration is real. Its effects are subtle on small scales, but over billions of years they dominate, determining the ultimate fate of the cosmos. If dark energy remains constant, expansion will continue forever. Galaxies drifting farther until only local groups remain visible. If it strengthens, it could lead to a big rip, tearing even atoms apart. If it weakens, gravity might eventually halt expansion and trigger collapse. Our measurements are not yet precise enough to decide. Webb contributes by refining the history of star formation and galaxy growth which depend on expansion. By anchoring distances more firmly and probing earlier epochs, it narrows the possibilities for dark energy's behavior. Combined with future missions, it may reveal whether this energy is truly constant or something evolving. The irony is that most of the universe is made of things we cannot see or fully explain. Ordinary matter, the atoms of stars and people, is only a small minority. Dark matter shapes the web. Dark energy shapes its destiny. Together they tell us that the cosmos is stranger than the intuition, yet more comprehensible each year as data accumulates. Dark energy forces us to accept that the largest structures in the universe are governed not only by gravity pulling inward, but also by a repulsion built into the fabric of space-time. Between these two, the universe's story unfolds a contest between attraction and acceleration, matter and mystery. Horizons in cosmology are not edges of matter. They are edges of influence, moving boundaries that decide which regions of the universe can ever share information. The simplest is the particle horizon, the current limit of what we can observe. It is defined by time, not by walls. Light has had only so long to travel, so we see only the sphere from which photons could have reached us since the first atoms formed and the fog cleared. Beyond that sphere, the universe likely continues, but its stories have not yet arrived. Another horizon is subtler and more unsettling. The cosmic event horizon. Because expansion is accelerating, there exists a distance beyond which light emitted today will never reach us no matter how long we wait. That horizon is a promise and a prohibition. It guarantees that some regions are forever out of causal contact with our future. The sky looks continuous, but its futures are divided into disjoint neighborhoods that can never talk again. Astronomers calculate these scales with the language of general relativity and the measured balance of matter and dark energy. The details are mathematical, but the message is plain. In a universe whose expansion accelerates, each observer lives inside a shrinking bubble of potential conversations. The most distant galaxies we can see today will fade beyond the event horizon in far future centuries, their light stretched into wavelengths too long to detect their histories, irretrievably separate from ours. This is not catastrophe. Nearby structures remain bound by gravity. The local group will survive as a single island, its stars continuing to orbit its remnants merging into a giant elliptical over eons, but the broader map thins out. Clusters that are today visible in our telescopes will dissolve from view, not because they vanish, but because the sea between islands rises faster than any ship can sail. Horizons also shape the temperature of the universe. As expansion proceeds, the cosmic microwave background cools its photons, diluted and stretched. In ages to come, it will slip from microwaves to radio, then to wavelengths so long that only instruments we have not yet imagined could catch them. The night sky will grow emptier, not because the cosmos is smaller, but because our share of it becomes a self-contained garden of stars drifting in darkness. When we talk about horizons, we talk about destiny. We talk about which signals can reach us and which we must infer from theory. We accept that some parts of the grand story will remain implied, not observed. That acceptance is not surrender. It is the discipline that lets us wring truth from the light we do receive, building a coherent narrative inside the boundaries that nature sets. In that coherence there is beauty, and in that beauty motivation to keep pushing the edges of sight. Horizons evolve. In the early universe, the particle horizon was small because little time had passed. As ages accumulated, it grew rapidly. The event horizon, by contrast, stabilizes in an accelerating cosmos, setting a permanent limit on what tomorrow can learn. Even neutrinos and gravitational waves which pass through matter easily face the same causal fences. No messenger outruns the shape of space-time. Our response to horizons is to diversify messengers while the sky is still generous. We build detectors for neutrinos and gravitational waves. We map polarization in the microwave background for ever fainter echoes, and we stretch radio arrays to hear the whisper of neutral hydrogen from the first billion years. Each method captures a different slice of the past before that slice recedes beyond practical reach. Horizons motivate a harvest season for knowledge, not despair. One subtlety often missed is that the so-called Hubble radius differs from both the particle and event horizons. It marks where recession speeds match light speed today, not forever. As the expansion rate changes, light can cross that radius in either direction. Naming these scales carefully prevents paradoxes and turns confusion into geometry we can reason about. The fate of the universe depends on a competition. On one side is gravity, the attraction of all mass and energy working to slow expansion and bind structures. On the other side is dark energy, a pressure of the vacuum that drives space to accelerate. Which side wins decides the ending. The data today favour an expanding future without end, a slow dimming known as the long freeze, but other possibilities linger at the margins of uncertainty. In the long freeze scenario, galaxies drift farther apart and star formation declines. Gas supplies are consumed or heated beyond easy cooling. The incandescent era of the universe gives way to a twilight ruled by long-lived red dwarf stars. These tiny suns burn their fuel miserly shining for trillions of years, far longer than the present age of the cosmos. Worlds around them will know epochs of stability our system cannot imagine, yet even red dwarfs will eventually exhaust their hydrogen. Darkness advances one extinguished star at a time. Another possibility is more dramatic. If dark energy were to grow stronger with time, the expansion could accelerate so violently that bound structures would be torn apart. This hypothetical future is called the Great Rip. First clusters would separate, then galaxies, then solar systems. In the final rush, even atoms would lose their grip. Observations so far do not demand this fate, but they do not absolutely forbid it. And so it remains a reminder that the properties of dark energy matter not just academically, but existentially. There is also the idea of a turnaround, a great crunch that would reverse expansion. For this to happen, the average density and the behavior of dark energy would need to tip the balance back toward collapse. Measurements make this outcome unlikely, yet cosmology is an experimental science. We read the sky and infer the rules. If future data alter the parameters, destiny would be rewritten. Each ending has its poetry. The long freeze is elegiac, a universe settling into quiet as stars wink out and black holes dominate the night. The Great Rip is apocalyptic, a crescendo of separation. The Great Crunch is cyclical, a return to heat and density that might precede another beginning. Our task is not to choose the story we prefer, but to measure the story we inhabit. The important truth is that the near future on human scales is stable. The Milky Way and Andromeda will merge in a few billion years. Star formation in our merged galaxy will continue for a long time. Planetary systems will rise and fall. Civilizations, if they endure, will watch new constellations form from tidal tails and starburst regions. Destiny is written in centuries of billions, but meaning is made now in the act of learning which line the universe is following. In the long freeze background, radiation cools toward absolute zero. Blackbody curves slide to longer wavelengths and stellar birth becomes sporadic as gas is locked in remnants or warmed by feedback. Giant molecular clouds still form here and there, and new stars will flicker into being, but the cosmic census tips inexorably from bright youth to dim maturity. Night skies slowly lose their dense tapestry and become sparser with more black between the surviving points of light. The geology of stars changes as well. Some white dwarfs will crystallize their interiors, forming lattices of carbon and oxygen. A handful might experience exotic reactions at extraordinary densities, theoretical whispers of late fireworks in the deep future. Neutron stars cool and quiet. Planets freeze. Orbits migrate under subtle tidal forces and encounters rewriting the architectures of aging systems. The stories differ in tone but share a moral. The second law of thermodynamics keeps the book. Energy gradients smooth away. Complex structures can persist by exporting entropy by tapping flows and contrasts, but the account eventually balances. Dark energy, if constant, accelerates this trend by diluting accessible matter and isolating islands of order. A universe of many little gardens replaces a universe of bustling trade. These far views can feel remote, yet they cast a clarifying light on the present. We live during the incandescent epoch when the sky is full, the background is warm enough to be measured easily, and the record of beginnings still hangs above us. Our instruments tuned to this moment can read the timeline from the first atoms to the rise of galaxies. Whatever the end, this is the golden age of understanding. It is the time to measure. Whatever global ending awaits, the late universe will be ruled by remnants. White dwarfs, neutron stars, and black holes will outlast their luminous progenitors. Over trillions of years, gravitational encounters will reshape galaxies. Some stars will be ejected into intergalactic space drifting alone. Others will spiral inward, feeding the central black hole or merging in faint flashes that briefly trouble the dark. White dwarfs are the exposed cores of sun-like stars, embers the size of Earth, packed with matter so dense that a teaspoon would weigh tons. They cool slowly, radiating away their stored heat. Given time beyond imagination, they will fade into black dwarfs, cold spheres barely distinguishable from the night around them. Whether protons endure forever or decay on unfathomable timescales will decide exactly how they end, but either way, the brightness wanes. Neutron stars, the collapsed corpses of massive suns, are denser still. A city-sized sphere holds more mass than the sun, its interior a quantum sea of neutrons. Some neutron stars whirl and beam lighthouses called pulsars. Others belong to binary pairs that will eventually merge, producing bursts of gravitational waves and forging heavy elements. These fireworks will be rare in the deep future, but not absent. The universe will not die all at once. It will exhale slowly with occasional sighs of brilliance. Black holes are stranger. They do not shine, but they shape everything around them. Eventually, even they may fade if the theory of Hawking radiation is correct. Quantum effects allow black holes to emit a trickle of particles losing mass at an incredibly slow rate. Small black holes would evaporate first. Supermassive ones would persist for time so long that words lose meaning before finally releasing a last whisper of heat and vanishing. In the far future, dynamics changes character. With few bright stars left, encounters become infrequent but not zero. Starless planets orphaned by gravitational kicks wander. Stellar remnants gather into loose associations and dissolve. The baryonic universe, once a blaze of structure, becomes a scattering of cinders under the rule of gravity and time. Galaxies themselves evolve under long gravity. A bound system slowly loses members through a process aptly named evaporation. Random encounters transfer energy. Some stars gain enough to escape. Over immense durations, only the most tightly bound objects remain. The central regions grow more dominant while halos thin. What began as a bustling city of stars becomes a quiet town, then widely spaced farmhouses, then empty road. Proton decay, if it occurs, would change the script. Some grand unified theories predict that even the most stable baryons have lifetimes so long that language falters. Should decay be real, black dwarfs would not persist forever. Their matter would gradually dissolve into lighter particles and radiation. Experiments on Earth show no sign within durations we can test, so the question remains open-filed under patience. Heavy element production continues in the meantime, sporadically. When two neutron stars merge, they fling out neutron-rich debris that cooks into gold, platinum, and rare Earth elements. Such clonovae will be scarce in the late universe, but their periodic glows will seed the darkness with new atoms, an echo of bygone alchemy. Even in decline, the cosmos can surprise. Cosmic rays, high-energy particles accelerated by shocks, and magnetic fields will fade as powerful accelerators shut down, but stragglers will continue to thread the void, a reminder that nothing ever truly reaches perfect stillness. Backgrounds remain. Relic neutrinos from the first second relic. Photons from the first few 100,000 years, relic gravity waves from mergers long past. The deep future is not empty of stories. It is simply quieter in their telling. To imagine such epochs is not morbid. It is a continuation of the same inquiry that lets us reconstruct the first minutes. Physics is time-symmetric in its ambition. If we can read the beginning from the sky, we can also read the end, at least in outline. Between those two horizons lies the era we inhabit, the thin, bright slice when stars are abundant and chemistry is adventurous. It is the window in which observers arise to ask what the whole arc looks like. Before the darkness, there is one last height of spectacle. The black hole era of mergers and tides. As galaxies combine, their central black holes sink toward one another through dynamical friction, stirring stars and gas as they go. Eventually they meet and merge, releasing vast energy as gravitational waves. Entire constellations could shift as orbits rearrange, tidal streams paint the sky, and new star clusters ignite in shocked clouds. Gravitational waves carry information differently from light. They travel through matter with near indifference, encoding the motions of massive objects directly in ripples of space-time. Future observatories designed for long wavelengths will be able to hear the bass notes of supermassive mergers across the universe. Each event will tell a chapter of galactic genealogy. When two families met, how much mass they shared and what kick sent the remnants spinning. Around the merged giant gas will settle into disks and feed the whole in bright episodes. Jets may launch, carving narrow beams that light intergalactic space. Feedback from these outbursts can quench or trigger star formation, sculpting the fate of the host galaxy. In this way, black holes act as both archivists and editors of cosmic history. Not all futures are quiet. Encounters between remnants can create exotic systems. Captured planets circling dead stars, triple black hole dances where one partner is flung away at tremendous speed. Hypervelocity. Stars slingshotted from galactic centers into the abyss. Each is rare. Together they guarantee that even a dim universe is not a static one. Listening for those stories is the task of a new generation of instruments. Space-based interferometers will fly in triangular formations millions of kilometers apart, measuring minute changes in arm length as waves pass. On Earth, long baselines listen at higher notes while networks of millisecond pulses time the slow rumble of giant mergers through correlated delays in radio pulses across the sky. Together, these observatories turn the universe into an audible landscape with chirps, hums, and roars that carry across cosmic time. Dynamical friction, the process that drags black holes together, deserves a moment of clarity. As a massive object moves through a sea of stars and dark matter, it leaves a wake. That overdense wake tugs backward, stealing orbital energy. Bit by bit, orbits shrink until gravitational radiation takes over and the plunge accelerates. Recoil kicks at merger can launch the remnant from the core, carrying a record of the final alignment of spins. Some galaxies may host off-center giants because of this, a hidden diaspora of displaced black holes. Jets launched by magnetic fields, coiled near spinning horizons, thread interstellar space. They inflate bubbles in hot gas, stir turbulence, and prevent runaway cooling. Without such feedback, central galaxies and clusters would turn their reservoirs into stars far too quickly. With feedback, the pacing steadies. Thus, the loudest objects in the universe also act as thermostats, regulating the temperature of their cities. The late era will feature quieter versions of these cycles, but the logic survives. Gravity gathers, orbits decay, mergers speak in waves, gas flows is heated and sometimes rains back. Astronomy shifts from bright pictures to precise timing, from imagery to a symphony of signals. The cosmic story keeps going, translated into a new medium as the old one fades. All of these fates presume that the laws we know endure, but what if the constants of nature drift or hidden particles alter the bookkeeping or new fields awaken as the universe cools? Cosmology is a measurement science. It leans on humility. We say what the data allow, we keep watching, and we build instruments to falsify our favourite stories. One frontier is the small tension between different ways of measuring the expansion rate today. Distance ladder methods anchored in nearby galaxies lean one way. Early universe inferences anchored in the microwave background lean another. The mismatch is small in percentage but large in meaning. It could be a systematic error hiding in dust corrections or calibrations. It could also be new physics, a brief episode of early dark energy, an extra light particle species, or a subtle change in how gravity behaves on large scales. Another frontier is the nature of dark matter. If it is a particle, how does it interact beyond gravity? If it is a field or a collection of black hole remnants, how would we tell? Experiments on Earth listen for faint recoils in underground detectors, while telescopes look for annihilation or decay signatures in the sky. So far the universe keeps it secret, but non-detection is a map too narrowing the options. Even the topology of space is open to test. Is the universe simply connected, or does it wrap in ways that could leave repeating patterns in the microwave background? Are there relics of primordial defects like cosmic strings that would lens background light into telltale lines? Observers have searched and not found decisive evidence, but the questions are sharp and sharper instruments are coming. Webb's role in these deep issues is indirect but crucial. By nailing down the timeline of early star formation, the buildup of metals and the abundance of small galaxies, it constrains how structure grew, which in turn constrains the physics that seeded it. Precision is cumulative. A better spectrum here and a cleaner distance there propagate through the equations, ruling out whole classes of models. Standard sirens add to the toolkit. When two neutron stars merge, their gravitational wave signal encodes the absolute distance independent of candles or ladders. If we also find a host galaxy and measure its redshift, we gain a fresh point on the expansion curve. A population of such events measured across time can weigh dark energy without relying on any single calibration chain. The promise is large, the patience required is larger. Another avenue is the 21 centimeter line of neutral hydrogen. As the first stars and galaxies formed, they heated and ionized their surroundings, imprinting fluctuations in this line across the young universe. Radio arrays aim to map these patterns statistically, turning the cosmic dawn and the epoch of reionization into three-dimensional movies. Combine those maps with galaxy surveys and microwave background measurements, and you tighten the weave of cosmology's net. Fundamental constants invite quiet tests. Atomic clocks on Earth compare transitions with exquisite sensitivity, looking for any drift in ratios over years. Quasar spectra provide the same test over billions of years as light passes through intervening gas clouds, whose lines encode physics long ago. So far the constants look constant. That in itself is a discovery, a confirmation that the laboratory and the sky share the same rules. Hints of cosmic birefringence alignments on the largest angular scales and other small anomalies keep theorists honest. Most will fade with better data. A few may bloom into real cracks. The discipline is to resist wishful thinking while also staying alert to the sky's surprises. In cosmology, as in all sciences, the universe gets the final vote. In the end, questions about fates and origins circle back to the same practice. Measure, compare, repeat. Build instruments that disagree with one another in constructive ways. Follow the tension, not the comfort. A cosmos this large will never be fully charted, but it can be increasingly well understood. The project is generational. That is its challenge and its grace. The Milky Way and Andromeda are destined to collide. In about 4 billion years, the two spirals will draw together under mutual gravity. Their halos of dark matter already overlap. From a distance, the encounter will look like two whirlpools merging arms, stretching stars flung outward into long streams. Inside, the drama will be less violent for individual stars because the gulf between them is vast. Collisions of suns will be rare, but the tidal reshaping will be spectacular. As they pass, gas clouds will crash and compress, triggering new starbursts. Entire clusters of young blue stars will blaze briefly. Then the galaxies will swing around each other, oscillating their shapes distorted into loops and shells. Eventually they will settle into a single massive elliptical, sometimes nicknamed Milky Way. Its disk will be gone, its spiral pattern erased, but its core will shine with a combined legacy of both families. During the merger, supermassive black holes at the centres will spiral inward. Their dance will radiate gravitational waves so powerful that even galaxies far away could feel tiny tremors in their timing. When the two holes merge, the outburst of energy will dwarf all starlight for a moment. The remnant will sit at the heart of Milky Way, a black hole tens of millions of solar masses in size. For any civilization still existing, then the night sky will change dramatically. Constellations will twist as Andromeda grows larger each century. Streams of stars will arch overhead like ghostly bridges. Nebulae of new stars will light the horizon. What is now a faint smudge in the northern sky will become a sprawling neighbour, then a partner in an embrace that lasts billions of years. Mergers like this are not rare. Most large galaxies have grown through such unions. The Milky Way itself shows scars. Stellar streams from cannibalized dwarfs, globular clusters of foreign origin. The great galaxies we admire today are mosaics, patchworks of many ancestors. What we will witness in our future is simply another stitch in the cosmic tapestry. These processes are part of the universe's metabolism. Gas falls inward, stars form, feedback blows some out, black holes grow, galaxies merge, and the cycle repeats. Each round enriches the mix of elements, builds complexity, and reshapes the map of light. Our galaxy's fate is not isolation, but integration, a reminder that nothing in the universe stands alone forever. When galaxies merge, clusters evolve as well. Clusters are not static cities, but dynamic arenas where galaxies orbit, collide, and sometimes escape. Over billions of years, dynamical friction drags massive galaxies toward the centre, building up a giant elliptical that dominates the cluster's heart. Smaller galaxies become satellites feeding the giant through mergers. The outskirts thin, the core thickens, and the cluster becomes more centrally concentrated. Meanwhile, dark energy alters the stage. As expansion accelerates, clusters become increasingly isolated. The filaments that once fed them thin out and inflow slows. In the far future, each cluster will resemble a cosmic island cut off from others by the growing gulf of expansion. The Virgo cluster, for example, will continue to evolve internally, but distant clusters will fade beyond reach, leaving Virgo as a self-contained world of hundreds of galaxies slowly fusing. Within clusters, hot gas remains a key player. It glows in X-rays, holds more mass than the stars, and acts as both reservoir and thermostat. Feedback from black holes and supernovae stirs it, preventing runaway cooling that would otherwise produce stars too rapidly. Without this regulation, clusters would shine more brightly than they do. The balance is delicate, a tug-of-war between cooling flows and heating outbursts. As time advances, star formation dwindles. Galaxies exhaust or expel their gas, becoming redder and quieter. Ellipticals dominate their populations, aging. Spirals fade. The cluster grows older, not just in age, but in colour, shifting from blue to red. Observers in the deep future would look upon a sky less varied with fewer glittering spirals and more uniform halos. Gravitational lensing, the bending of light by cluster mass, continues to reveal secrets. Arcs of background galaxies wrap around cluster cores magnified by the intervening mass. These lenses act as telescopes, letting us glimpse galaxies far beyond our direct reach. In the accelerating future, when many sources fade, such natural telescopes may remain the only tools to study what still lies barely within sight. Clusters are therefore paradoxical, internally dynamic yet externally stranded. They are the last great gatherings in a universe of increasing solitude. The Virgo cluster will merge into a single colossus while others follow suit. Each becomes a monument to gravity's tenacity, holding together while the broader cosmos slips away. Gravitational lensing does more than magnify. It encodes the distribution of matter. By mapping the distortions in arcs and sheared images, astronomers can reconstruct the invisible scaffolding of dark matter. This technique, called weak lensing, when applied to many subtle distortions at once, has become one of the strongest probes of cosmic structure. Strong lensing, by contrast, creates dramatic arcs, rings, and multiple images. A single quasar may appear as 4 points arranged around a lensing galaxy. Time delays between flickers in those images measure cosmic distances, directly adding to the ladder of methods that pin down expansion. Each lens is both a telescope and a ruler, magnifier, and metric. On larger scales, surveys of weak lensing patterns across millions of galaxies map the growth of structure through time. By comparing these maps to predictions, cosmologists test whether gravity behaves as expected. Deviations could hint at modifications to general relativity or new interactions in the dark sector. So far the agreement is good, but small tensions keep interest alive. In practice, lensing provides natural laboratories. Some of the earliest galaxies discovered owe their visibility to lensing magnification. Light that would otherwise be too faint to register is stretched and brightened by intervening clusters. Webb's deep fields often exploit this trick, aiming through massive foreground structures to amplify what lies behind. In this way, gravity itself helps us see farther. Future observers, when the universe is older and fainter, may rely on lensing even more. While galaxies drift beyond reach, their light already en route will continue to pass through cluster lenses, arriving magnified. For a time, the combination of cosmic patience and gravitational optics will extend the era of discovery. Eventually, even that supply will dwindle, but not before we have read many additional chapters. Lensing is therefore not just a curiosity, but a central method. It ties together geometry, growth, and dark matter. It transforms clusters into instruments and turns chance alignments into opportunities. It shows that even the distortions of light are data, and that beauty in the sky can also be measurement. Astronomy is entering a new age of multi-messenger observation. For centuries, light was our only messenger, spanning radio to gamma rays. Now gravitational waves, neutrinos, and cosmic rays join the conversation. Each tells a different story. Together they weave a richer tapestry of cosmic events. The merger of two neutron stars in 2017 was a turning point. Gravitational waves announced the collision. Seconds later, gamma-ray bursts flared. Hours later, optical telescopes found the kilonova glowing with freshly forged elements. Radio telescopes tracked the afterglow as jets ploughed through surrounding gas. Never before had we watched one event in so many messengers. The result confirmed theories of heavy element creation and demonstrated the power of coordination. Neutrinos offer another channel. These nearly massless particles slip through matter with ease. A single supernova in our galaxy would shower detectors with neutrinos hours before its light arrives, providing early warning and insight into the collapse. Cosmic neutrinos from distant blazars have already been detected, tying high-energy particles on Earth to engines light years away. Cosmic rays, though charged and deflected by magnetic fields, still carry information about accelerators like supernova remnants and active galaxies. They link local processes to high-energy astrophysics. When combined with light waves and neutrinos, they complete the set of messengers that cross-check one another, eliminating ambiguities. Future observatories will deepen this approach. Next-generation gravitational wave detectors will hear fainter and more distant mergers. Kilometre-scale neutrino arrays will catch rarer cosmic events. Wide-field optical telescopes will respond rapidly to triggers. The synergy is intentional. No single messenger tells the whole story, but together they constrain models tightly. Multi-messenger astronomy is more than technique. It is philosophy. It assumes the universe speaks in many voices and that progress comes from listening to them together. It democratizes data, turning every event into a global collaboration. When the sky flashes, detectors around the world coordinate, each adding a piece to the puzzle. The result is not just a richer science, but a more resilient one. The future may bring messengers we have not yet recognized. Exotic particles, new fields, or unknown signals could open channels. The lesson from the past is to remain open. Each time we add a new messenger, the universe surprises us with clarity we did not expect. The long arc of cosmic history, from quantum ripples to merging galaxies, suggests a unity of process. Yet each scale introduces fresh questions. The physics of inflation links quantum fields to cosmic geometry. The growth of the Webb links dark matter to ordinary gas. The late era links dark energy to destiny. Across these bridges, one principle endures. The universe evolves, and evolution writes complexity from simplicity. Cosmic history is not linear, but layered. At any given time, multiple processes unfold at once. Stars live and die, galaxies merge, clusters accrete, expansion accelerates. Each leaves imprints in light waves and particles. Reading those imprints requires theory, simulation, and observation to align. When they do, the result is coherence. When they do not, the result is tension, which signals the next frontier. Humanity's role is to gather coherence while leaving room for tension. Instruments like Webb extend the reach of light. Detectors of waves and neutrinos extend the reach of messengers. Simulations extend the reach of imagination, showing what theories predict under different assumptions. Together they narrow the field of possibilities. In practice, progress is uneven. Some questions yield clean answers. The age of the universe, the existence of dark energy, the broad picture of structure formation. Others resist. The identity of dark matter, the true nature of inflation, and the ultimate fate of expansion. This unevenness is not a flaw, but a map of where effort is needed. It is how science advances, by finding the sharp edges where data and theory diverge. The cosmic perspective has a strange effect. It both humbles and empowers. It shows us that our planet is a speck in a vast arena. Yet it also shows that we can comprehend arenas far beyond direct experience. Equations written on chalkboards describe processes billions of light years away. Photons that left before Earth formed land in our telescopes and confirm those equations. This coupling of small and large, near and far, is one of the marvels of science. Looking ahead, the project is clear. We will refine distances, map structures, listen for waves and trace messengers. We will tighten constraints on dark energy, probe deeper into ionization, and watch galaxies at the moment of their first light. We will keep building coherence and chasing tension. The universe offers both endlessly. The story does not end with an answer. It ends with a method. Measure carefully, compare honestly, adapt willingly. That method has already carried us from myths of static heavens to precise chronologies of 13.8 billion years. It will carry us farther still. As the universe evolves, the sky itself will change for future observers. Already expansion alters what is visible. Galaxies beyond a certain redshift fade, their light stretched until it slips out of detectable bands. Instruments like Webb are tuned to capture those faint whispers in infrared, but eventually even those will be gone. Civilizations living trillions of years from now would find themselves in a different kind of cosmos, one where most galaxies have slipped beyond the event horizon, leaving only local structures to study. For them, astronomy would look provincial. The Milky Way and its descendants, perhaps the merged giant of Milkomeda, would be all that remains in sight. The cosmic microwave background, once a luminous relic for us, will have stretched into wavelengths far longer than any natural detector can register. The primary evidence for the Big Bang will be gone. Without records preserved, they might never deduce that their universe was once ablaze with galaxies and light. Even today, the sky carries reminders that knowledge is time-sensitive. The photons Webb captures have travelled billions of years. They show us galaxies that no longer exist in that form. Their stars may have already died, their gas reshaped, but the images remain as fossils. We are peering not into distance alone, but into the past. Astronomy is a kind of archaeology, except that the artifacts arrive freshly each night. The fading of distant galaxies is not just a theoretical concern. Already some objects are at the edge of detectability. Webb's deep fields reach galaxies less than 500 million years after the Big Bang, but not all sources are visible. Some are too faint, some too obscured by dust, some too far redshifted. Even with perfect instruments, horizons impose absolute limits. We see a slice of the universe, not the whole. This creates urgency. We live in a privileged epoch when both the microwave background and the earliest galaxies are accessible. We can measure expansion while structures are still forming. We can test inflation against its imprints. Future observers marooned in a darkened cosmos will not have these luxuries. They may never confirm dark energy or inflation. They may never see evidence for the cosmic web beyond their local cluster. Our knowledge, therefore, is both cumulative and fragile. It depends on being at the right time with the right instruments. The irony is that our moment brief in cosmic terms is uniquely informative. We arrived at a cosmic noon of star formation, close enough to the dawn to see its light late enough to measure the fate of expansion. From here we can stitch together a full story that no future epoch will replicate. What tools remain when the obvious messengers fade? Advanced civilizations might attempt to capture signals that survive the dimming. Neutrinos, for example, pervade the cosmos nearly massless and barely interacting. Relic neutrinos from the first second after the Big Bang still drift through space, a cosmic sea colder than the microwave background. Detecting them is beyond current technology, but not beyond imagination. Instruments vast and sensitive enough could one day catch these ghosts, providing a snapshot of the universe's first heartbeat. Gravitational waves also persist. Unlike photons, they are not redshifted out of range in the same way. They carry direct information about violent processes, mergers of black holes, collapse of stars, perhaps even echoes of inflation itself. Though weaker over time, they remain traces of dynamics across the universe. A far future civilization could listen to the deep bass of space-time long after light has faded. There are also clever uses of local relics. Isotopes on planets carry records of cosmic ray bombardment. Geological strata encode the rhythm of supernovae near our system. Even the orbits of comets and asteroids reflect long-term gravitational tides from galactic encounters. By reading local evidence, astronomers can reconstruct parts of cosmic history, even if distant sources vanish. Another path is theoretical. Once laws are established, they can be extrapolated. If general relativity holds, then horizons and expansion are predictable. If the cosmic microwave background is lost to direct detection, its properties could still be inferred from models tested earlier. Physics allows us to bootstrap from fragmentary evidence to global stories. That is why today's measurements matter not just for us, but for any future heirs of science. Still, limits remain. No matter how clever, no method can restore information that lies forever beyond the event horizon. Some stories will be cut off. The challenge is to extract as much coherence as possible before the shutters close. That is why missions like web ground surveys and multi-messenger observatories represent not just curiosity but urgency. We are gathering pages before the book drifts out of reach. This realization reframes cosmology. It is not a leisurely exploration of eternal truths, but a race against horizons. Each photon collected now is irreplaceable. Each gravitational wave detection adds permanence to memory. We are archivists of the sky, and the archive is time-sensitive. Imagine the sky of the far future. Milky Way dominates a swollen elliptical with few spirals left. The night is quieter, punctuated by red dwarfs and aging remnants. No nearby clusters are visible. Expansion has erased them from sight. Astronomers, if they exist, chart only their home system and a handful of satellites. The broader web is gone. For them, cosmology becomes local. This future sky is not fiction, but extrapolation. Equations predict that beyond a certain time, the observable universe contracts in practical terms, not because the cosmos shrinks, but because access shrinks. Signals redshift sources fade, evidence disappears. The laboratory becomes provincial. A scientist in that era, without historical records, might conclude the universe is static and small. Only by inheriting our data could they know otherwise. There is poignancy here. We live at a time when the universe is both vast and legible. Our telescopes see billions of galaxies. Our detectors hear waves across space-time. Our theories connect quantum scales to cosmic ones. This dual accessibility is temporary. Like twilight, it will pass. That makes our project urgent and our knowledge precious. And yet the far future is not entirely bleak. Within Milky Way, stars continue to form, albeit slowly. Stellar remnants interact, black holes merge, planets orbit. Local astrophysics endures. Life, if it persists, will have new skies to interpret. Their myths and sciences will adapt to the diminished view just as ours adapted to what we could see before telescopes. They will not be bereft, only bounded. Our role then is to preserve. Data recorded now may become the Rosetta Stone of the cosmos for those who come later. Archives on durable media signals broadcast into interstellar space, perhaps even etched on interplanetary monuments, all could carry forward the knowledge that the universe was once measured as vast and dynamic. Memory may become the greatest gift we leave. The idea of preserving cosmic knowledge leads naturally to speculation about interstellar archives. If civilizations rise and fall, if horizons close, then continuity of science depends on redundancy. Imagine libraries on multiple planets, vaults of data buried in asteroids or probes dispatched beyond the galaxy carrying records. Each would act as a seed, ensuring that even if one culture falters, the story survives. Already humanity has begun this in modest ways. The Voyager spacecraft carry golden records with sounds and images of Earth. Radio signals have spilled into space for a century. Archives on the Moon and Mars are planned by some groups designed to outlast terrestrial catastrophes. These are small steps, but they echo a larger instinct: to share and preserve. In cosmic terms, preservation is a form of resistance. Entropy erases, expansion isolates, scarcity. But information carefully stored and redundantly copied can persist. A future civilization, perhaps billions of years hence, could stumble upon such archives and rediscover truths long hidden from direct observation. They might learn that galaxies once filled the sky, that a microwave glow once bathed the cosmos, that expansion once revealed its secrets. Even without life, archives could outlast us. A probe drifting in intergalactic space carrying etched plates of data might survive for eons unaffected by erosion or atmosphere. It would be unreadable without context, but so are fossils until deciphered. What matters is survival. Decoding can come later. Preservation is also humility. It accepts that our epoch is not permanent, that knowledge has windows. By archiving now, we extend the reach of those windows. The very act of measurement gains weight when we recognize its impermanence. To know that we are gathering the only comprehensive record the universe will ever allow is sobering and motivating. Limits on observation are not limits on imagination. Physics invites thought experiments that test what might be possible, even if impractical. Could an advanced civilization manipulate space-time itself to see beyond horizons? Wormholes, for example, are solutions to Einstein's equations that connect distant regions. If they exist and can be stabilized, they could bypass cosmic limits, providing shortcuts through space and time. Whether nature allows this remains uncertain, but the equations permit speculation. Another idea is to use black holes as telescopes. Their gravity bends light into extreme arcs. A civilization could place detectors at the focal points of these natural lenses, magnifying distant sources enormously. In theory, the sun itself could act as such a lens, focusing light from background stars at distances of hundreds of astronomical units. Projects have proposed probes to exploit this, though practical challenges are immense. Some speculate about engineering new messengers. Could space-time vibrations be generated deliberately and tuned like signals? Could exotic particles less affected by expansion be harnessed as carriers of information? These are beyond current science, but they demonstrate the principle that limits are invitations to creativity. Horizons set boundaries. Physics asks how those boundaries might be crossed. Still, caution is required. Not every equation corresponds to reality. Wormholes may be unstable. Exotic particles may not exist. But by exploring the edges of possibility, we learn the contours of the permissible. Even failed ideas sharpen knowledge by showing what cannot be. Cosmology thrives on this interplay between audacity and discipline. What matters is that the universe is not a closed book. Even as horizons limit direct access, indirect inference, theoretical extrapolation and creative engineering remain paths forward. The story of science is not about reaching final answers, but about extending reach one method at a time against the retreat of information. Among the boldest frontiers in cosmology is the possibility that our universe is not the only one. Eternal inflation, an extension of the inflationary theory, proposes that the rapid expansion, which smoothed our cosmos, may never have stopped everywhere. Instead, pockets of space continued to inflate while other regions cooled and stabilized. Each stabilized bubble could become its own universe with its own laws of physics. We live in one such bubble, surrounded not by galaxies but by other universes beyond any horizon we can reach. The mathematics of eternal inflation is seductive. Quantum fluctuations in the inflationary field mean that while some regions slow and end inflation, others are kicked into further expansion. The result is a fractal multiverse endlessly budding like foam on an ocean. Within this picture, our universe is not unique but one sample from a cosmic ensemble. Constants, we measure the strength of gravity. The charge of the electron, the density of dark energy may be environmental accidents, differing in other bubbles, where physics plays by alternate rules. Observationally testing this is daunting. By definition, other universes lie beyond causal contact, yet some argue that collisions between bubbles might leave imprints, circular scars in the microwave background, subtle anomalies in temperature maps. Searches have been made. No convincing evidence has yet appeared. Still, the possibility motivates sharper analyses because even null results constrain models. The philosophical shift is dramatic. Instead of asking why the constants of nature have the values they do, eternal inflation allows the answer. Because they can, and only certain ranges allow life. The anthropic principle, controversial but persistent, gains footing here. Our universe is habitable not because of necessity, but because countless others are not. Critics point out that unfalsifiable theories risk stepping outside science, yet eternal inflation remains anchored in equations already successful at describing the early cosmos. Whether it is real or not, exploring its implications sharpens our sense of what the data must show if the idea is to hold. Linked to eternal inflation is the concept of the multiverse. If many universes exist, how do we classify them? Some models imagine a level 1 multiverse, simply regions of our own space beyond the observable horizon, identical in physics but forever inaccessible. A level 2 multiverse arises from eternal inflation, with bubbles that may have different constants and even different numbers of dimensions. Level 3 corresponds to the many worlds interpretation of quantum mechanics, where every quantum event spawns a branching universe. Level 4 stretches further, encompassing all mathematically possible structures. The taxonomy may sound speculative, but each level arises from attempts to solve real puzzles. Inflation demands something beyond our horizon. Quantum mechanics already treats probability as reality and waiting. Mathematics has long hinted that our universe could be just one example in an infinite space of forms. The multiverse is not invention out of nothing, but extrapolation from theories that work locally. Testing remains the challenge. Some levels like level 1 are almost trivial if space is infinite. Then beyond our horizon lie regions we cannot see but which exist nonetheless. Others like level 2 may leave indirect clues in the form of variations in constants or signatures of bubble collisions. Levels 3 and 4 are more philosophical, pressing the boundary between physics and metaphysics. Still, the conversation matters. By asking whether our universe is unique, we probe the assumptions baked into our models. We examine whether fine-tuning is illusion, whether constants must be explained or simply accepted as environmental facts. We stretch imagination, but not arbitrarily, always tethered to the scaffolding of established physics. Hidden dimensions are another possibility that emerges naturally from attempts to unify physics. String theory. One of the leading candidates proposes that fundamental particles are not points but vibrating strings, their resonances producing the particles we observe. For the mathematics to work, extraspatial dimensions are required 6 or 7 beyond the 3 we know curled up so tightly that we cannot perceive them directly. If true, these hidden dimensions might influence cosmology. They could alter how gravity behaves on very small or very large scales. They could provide explanations for why fundamental constants take their values. They might even allow energy to leak between dimensions, producing signatures in experiments. Searches for deviations in gravity at short distances or for exotic particles that betray extra-dimensional origins are ongoing. In the cosmic context, hidden dimensions could leave marks in the early universe. Inflation might be shaped by fields that exist partly in these unseen spaces. Dark matter could be a particle stabilized by extra-dimensional symmetries. Even dark energy might find explanation in the geometry of hidden realms. Direct evidence remains elusive. No particle accelerator has yet seen signs of strings or extra dimensions. But the ideas persist because they knit together gravity and quantum mechanics in ways that otherwise resist unification. If discovered, they would transform cosmology, showing that our three-dimensional view is only a shadow of a larger stage. Speculation about extra dimensions and multiverses often prompts criticism. How can science claim progress if its ideas are untestable? The answer is discipline. Theories must eventually touch data. Even if hidden dimensions are small, they could affect the properties of particles we can measure. Even if other universes are beyond reach, their physics could leave traces in ours in the form of anomalies, constants, or patterns. The task is to sharpen predictions until they meet experiment. This discipline has precedent. Black holes were once theoretical curiosities doubted for lack of evidence. Today, we image their shadows and record their mergers in gravitational waves. Neutrinos were proposed as bookkeeping devices in nuclear reactions, invisible for decades until detectors confirmed them. Cosmology thrives on patience, testing bold ideas across generations. Meanwhile, speculation fuels creativity. Thinking about multiverses pushes us to consider what counts as an explanation. Thinking about extra dimensions forces us to test gravity in regimes we once ignored. Even if the final answers differ, the pursuit sharpens both instruments and minds. All these explorations, multiverse, inflation, hidden dimensions, converge on a single theme. The universe may be larger and stranger than the part we see. Our observable horizon is not the boundary of reality, but only of access. Beyond it could lie replicas, variations, or deeper structures. Whether or not we ever prove their existence, grappling with them deepens our grasp of what universe means. In practice, cosmology advances by alternating between daring ideas and careful measurements. We imagine bubbles beyond sight, then check the microwave background for scars. We propose hidden dimensions, then measure gravity with exquisite precision. We speculate about new particles, then build detectors underground or in space to catch them. Most ideas will not survive, but some will. The survival rate is less important than the rigor of the trial. The result is a science that is both humble and ambitious. Humble because it accepts uncertainty and embraces failure. Ambitious because it dares to describe everything from the birth of time to the fate of galaxies. This tension is the source of cosmology's vitality. Astronomy has always advanced through new instruments. Each leap in sensitivity or wavelength has revealed surprises, often overturning expectations. The next generation of telescopes continues this tradition. Giant optical observatories on Earth, like the extremely large telescope in Chile, will host mirrors 30 to 40 meters across. Their resolution will rival or surpass that of Webb, though limited by Earth's atmosphere. With adaptive optics correcting distortions in real time, they will pierce deeper into crowded starfields, measure exoplanet atmospheres, and map the faint outskirts of galaxies. Space remains the ultimate laboratory. Freed from atmospheric turbulence and absorption, space telescopes offer clarity no ground-based system can match. Concepts, already under development, imagine successors to Webb with even larger mirrors segmented and folded for launch, then deployed into precise configurations. Coronagraphs and star shades could block stellar glare, letting faint planets appear against their suns. Infrared, ultraviolet, and X-ray missions will complement one another, producing a full-spectrum view of the cosmos. Beyond single telescopes lies interferometry. By linking many smaller instruments across great distances, astronomers can synthesize the resolution of a much larger aperture. Radio astronomers already use this method to map distant quasars with micro-arc-second precision. Future space-based arrays could apply the same principle in optical and infrared, building telescopes the size of Earth's orbit. Such systems could resolve surfaces of stars, watch planets in other systems as disks rather than dots, and even detect continents on exoplanets. The ambition is staggering. These instruments would not simply extend current knowledge, they would change what counts as observable. Worlds once speculative could be mapped directly. Galaxies once faint smudges could be dissected star by star. The universe would step closer, detail replacing blur, certainty replacing inference. Gravitational wave astronomy is also poised for transformation. Current detectors like LIGO and Virgo have already recorded dozens of mergers of black holes and neutron stars. Their kilometre-scale arms measure changes smaller than a proton's width. But they are only the beginning. Future observatories will be vastly more sensitive and broad in frequency. The planned space-based interferometer, LISA the Laser Interferometer Space Antenna, will consist of 3 spacecraft flying millions of kilometers apart, forming a triangle in orbit around the Sun. Laser beams exchanged between them will measure distortions caused by passing gravitational waves. Unlike ground detectors, LISA will hear the low-frequency notes, the slow-in spirals of supermassive black holes, the chorus of compact binaries across the galaxy, and perhaps even the faint background hum from the early universe. On Earth, next-generation detectors like the Einstein Telescope in Europe and Cosmic Explorer in the United States aim to dig deeper into the high-frequency range. Their longer arms and advanced isolation systems will detect weaker signals, capturing tens of thousands of events per year. With such numbers, statistical studies become possible, mapping black hole populations, measuring neutron star interiors, and probing the expansion of the universe with standard sirens. Gravitational waves complement light. Where photons can be absorbed or scattered waves pass through, they offer direct access to regions otherwise hidden. The cause of mergers, the collapse of massive stars, the dynamics of space-time itself. As the catalogue of events grows, patterns emerge, teaching us how galaxies assemble, and how often stars end in compact remnants. The dream is to one day detect primordial gravitational waves, ripples stretched from inflation itself. Such a detection would confirm theories about the earliest fractions of a second and link quantum physics to cosmic expansion. Whether through polarization of the microwave background or direct measurement of the gravitational wave background, this remains one of the holy grails of cosmology. Another frontier is the search for exoplanets and biosignatures. The past 3 decades have revealed thousands of planets orbiting other stars, Most were found indirectly through dips in starlight or tiny wobbles in stellar motion. The next era aims at direct characterization. Large space telescopes with coronagraphs will block starlight to reveal planetary light. Spectroscopy of these faint worlds will identify molecules in their atmospheres, water vapor, methane, oxygen, carbon dioxide. Detecting such signatures is not simple. Many molecules can arise from non-biological processes. Distinguishing true biosignatures from false positives requires context. The balance of gases, the chemistry of the surface, the energy from the star. But even the possibility of detecting life beyond Earth is revolutionary. For the first time, we could compare biology across worlds, seeing whether life is common or rare in the cosmos. Future concepts include star shades, giant structures flying tens of thousands of kilometers from a telescope, precisely aligned to block a star's light while letting the planet shine. If engineering succeeds, entire planetary systems could be imaged in detail. Instead of single spectra, we could watch weather on exoplanets, track seasonal changes, and perhaps even glimpse surface features. The implications ripple through cosmology. Life, if detected, becomes part of the cosmic narrative. Stars make elements. Planets assemble, chemistry turns to biology, and biology turns into observers who reflect on the process. Whether life is common or unique, the answer reshapes our understanding of the universe's story. Cosmology also depends on radio eyes. The square-kilometre array, now under construction in South Africa and Australia, will be the largest radio telescope ever built. Its vast collecting area will make it exquisitely sensitive to faint signals. One of its primary goals is mapping the universe in the 21-centimetre line of neutral hydrogen. This line emitted when the spin of the electron in hydrogen flips carries information about gas in galaxies and between them. By surveying billions of galaxies, the square-kilometre array will trace the large-scale structure with unprecedented detail. It will map the cosmic web track baryon acoustic oscillations and titan measurements of dark energy. It will also probe the epoch of reionization, when the first stars and galaxies ionize the hydrogen fog, turning the universe transparent. By capturing the faint glow of hydrogen before and after this transition, we will reconstruct the dawn of structure. The array will also search for cosmic magnetism, pulsars, and even signals from extraterrestrial intelligence. Its scale allows it to time pulsars with such precision that gravitational waves from supermassive binaries could be detected through correlated delays. In this way, radio astronomy contributes not just to astrophysics but to fundamental physics. Looking farther ahead, astronomers dream of instruments beyond Earth's orbit. Telescopes stationed at the stable gravitational points known as Lagrange points already provide stable platforms. But even larger projects are conceivable. Imagine a flotilla of mirrors spread across thousands of kilometers phased together into a single instrument. Such an array could directly image the surfaces of distant stars or resolve continents on nearby exoplanets. Another vision is lunar observatories. The far side of the moon is shielded from Earth's radio noise, making it a pristine site for low-frequency radio telescopes. Arrays built into lunar craters could map the early universe in wavelengths inaccessible from Earth. The moon's stability and vacuum also make it attractive for optical interferometers. Space also offers gravitational quiet. Instruments flying in formation can measure with extreme precision, untroubled by seismic noise or atmosphere. Future generations might place interferometers around the Sun, or even across planetary orbits, synthesizing apertures of unimaginable size. Each step would peel back another layer of detail, shrinking uncertainty and expanding reach. The long arc of these plans shows a truth. Curiosity drives engineering. We build what seems impossible because the universe demands it. Each time we push the frontier, the cosmos rewards us with surprises. The unknown is not empty, but fertile, waiting for the right lens, the right ear, the right imagination. Dark energy remains the most baffling ingredient in the cosmic recipe. It was discovered not through direct detection, but through the dimming of distant supernovae, which revealed that expansion is accelerating rather than slowing down. Since then, every line of evidence, cosmic microwave background, baryon, acoustic oscillations, growth of structure has confirmed its existence. Yet what it is remains a mystery. Is it a property of space itself, an irreducible vacuum energy? Or is it a dynamic field evolving with time? The stakes are high. Each possibility carries different implications for the fate of the cosmos. If dark energy is truly constant, the universe will continue to accelerate forever. Galaxies not bound to our local cluster will slip away beyond our horizon, leaving only our island of stars. If instead dark energy evolves, stranger fates await. A phantom, like energy with equation of state less than negative, one could grow stronger with time, eventually tearing apart galaxies, stars, and even atoms in a big rip. A weakening field might fade, allowing gravity to slow expansion, or even reverse it, leading to a collapse. The data so far favour constancy, but small uncertainties keep all scenarios alive. To probe deeper, astronomers map galaxies across ever larger volumes. By measuring how structures grow over time, they infer the push and pull of dark energy. Surveys like the Dark Energy Spectroscopic Instrument and future missions like Euclid and the Nancy Grace Roman Space Telescope aim to chart tens of millions of galaxies, creating three-dimensional maps that reveal the fingerprints of acceleration. Combined with lensing and supernova studies, these will tighten constraints on the equation of state parameter testing, whether it deviates from -1. At the same time, theorists explore radical possibilities. Could dark energy be linked to quantum fluctuations of space-time? Could it arise from interactions between hidden fields? Could it signal a breakdown of general relativity on cosmic scales? Each idea is bold, some verging on speculative, but all remind us that ignorance is fuel. Where we lack clarity, creativity multiplies. For now, dark energy remains an enigma hiding in plain sight, invisible yet dominant, elusive yet shaping the destiny of everything we see. The hunt for dark energy has reshaped not only cosmology but also technology. Building surveys that cover a third of the sky requires detectors with wide fields, sensitive spectrographs, and supercomputing pipelines capable of processing petabytes of data. These advances ripple outward, benefiting other sciences from climate modelling to genomics. In this sense, the mystery of cosmic acceleration acts as an engine of innovation. But the deeper motivation is existential. To know dark energy is to know the long-term fate of the universe. Imagine living under a Big Rip scenario, every structure doomed, time horizon shrinking until even molecules cannot survive. Or consider a slow fade where galaxies dim and drift into eternal isolation, the night sky growing poorer with each passing billion years. These are not abstract outcomes, they are our true inheritance as part of the cosmos. Gravitational wave detectors may join the quest. Standard sirens, the inspirals of neutron stars and black holes, provide distance measures independent of light. By comparing their distances to redshifts, astronomers can map expansion directly. Already the first events hint at this potential. With thousands of detections per year in the future, standard sirens will become rivals to supernovae as cosmic yardsticks. Neutrinos and radio surveys also contribute. Fast radio bursts, mysterious millisecond flashes, can be used as probes of the intergalactic medium. Their dispersion measures reveal how much matter lies along the path, helping to close the missing baryon problem and providing additional leverage on cosmic expansion. Together, these efforts weave a net tighter around dark energy. Whether it proves to be constant or variable, geometric or field-like, we will not stop until its mask is removed. And when that day comes, the answer may force us to rethink what space-time itself really is. Multi-messenger astronomy is poised to expand this search. Already we have seen how combining light and gravitational waves confirm the origin of heavy elements. The same principle can be applied to cosmology. Gravitational waves provide absolute distance scales. Light provides redshift. Together they build the expansion history in stereo cross-checking one another. The future promises a network of messengers so rich that no event will go unseen. Neutrino detectors kilometers underground will catch the faint streams from collapsing stars. Gamma-ray satellites will register bursts across the sky. Optical telescopes will spin instantly to the coordinates, capturing afterglows within minutes. Radio arrays will map the jets as they interact with interstellar gas. Each messenger supplies a different angle together, forming a complete portrait. Such synergy is vital for the deep questions. To pin down dark energy, to test modifications of gravity, to probe the interiors of neutron stars, no single messenger suffices. Each brings strengths and weaknesses, but together they cancel biases and sharpen clarity. This is the philosophy of the 21st century sky. Collaboration, not only among people but among particles. In the far future, when light sources fade, some messengers may persist longer. Gravitational waves less affected by expansion may continue to carry information when photons have stretched beyond detection. Neutrinos nearly impossible to block will still whisper the story of cataclysms. By investing now, we prepare a toolkit not only for our era but for those to come. Multi-messenger astronomy is not just method but survival strategy for science. It ensures that as one channel dims, another remains open. The universe may grow quieter, but it will never fall entirely silent as long as we keep listening in every possible way. Yet the silence will grow. Already distant galaxies are receding faster than light relative to us, carried by expansion. Their signals, though emitted, will never arrive. Each year another shell of galaxies slips past the horizon. In trillions of years, only the local cluster will remain visible. This cosmic isolation is not metaphor but fact, written in the equations of general relativity and confirmed by observations of acceleration. What does science look like in such a future? Without distant galaxies, without the microwave background cosmology as we know it, would be impossible. Civilizations then would deduce a static universe, small and local, unless they inherited archives from us. This is why our moment is precious. We live at a time uniquely rich in information. Some have suggested creative methods for future astronomers. Artificial probes could be launched now orbiting stars for trillions of years, carrying data on the early cosmos. Civilizations could use black holes as natural archives, dropping signals into stable orbits where they would persist. Even within isolation, knowledge could endure if only someone prepares it in advance. For us, the fading of the sky is a spur. It drives urgency in building observatories, in recording data and archiving results. We are not simply exploring, we are preserving. Each spectrum, each map, each signal caught is a message to the future, a statement that once the cosmos was wide open and full of light. Science thrives on tension between what we know and what we cannot yet know. Dark energy exemplifies this. We see its fingerprints in every map of galaxies, yet its nature evades capture. Multi-messenger astronomy exemplifies this. We glimpse its potential, yet we are still building the networks. The fading cosmos exemplifies this. We enjoy abundant signals now, but we know they will dwindle. Each tension is not despair, but direction. Our response is resilience. We invent new detectors, link new messengers, and imagine new theories. We confront horizons not by surrendering, but by pushing against them with creativity and patience. If the universe denies us photons, we listen for waves. If it hides signals in noise, we build instruments to sift them out. If it confronts us with silence, we leave records so that silence is not final. This resilience is the hallmark of science across centuries. When stars were thought eternal, astronomers measured parallax and proved otherwise. When galaxies were thought nebulae, telescopes revealed their distances. When expansion was thought to slow, supernovae revealed acceleration. Each time the universe overturned assumptions, and each time we adapted, the pattern will continue. In this way, the story of cosmology is not only about the universe but about us. It is a story of minds reaching outward of societies, investing in tools that outlive their builders of curiosity, defying isolation. Whether or not we ever fully solve dark energy, whether or not we ever touch other universes, the pursuit itself is triumph. It binds us to the cosmos with threads of inquiry, fragile yet enduring. Entropy is the quiet law that governs the long future of the universe. Every star that shines, every black hole that feeds, every galaxy that collides increases disorder. Locally order blossoms, stars forge elements, planets give rise to life, civilizations build cities. But globally, the trend is inexorable. Energy spreads, temperature differences even out. The cosmos moves steadily toward thermal equilibrium, a state where no useful work can be done. This is the heat-death scenario, and it remains one of the most widely accepted fates of the universe. In the nearer term, stars will exhaust their fuel. Red dwarfs, the longest-lived, may burn for trillions of years, glowing dimly while heavier stars fade. White dwarfs will cool, to black neutron stars will spin down, and black holes will dominate. Already we see glimpses of this transition in galaxies where star formation is nearly finished. They are previews of the universal senescence to come. Entropy also governs information. Structures that record memory, from geological strata to biological DNA, decay. Over cosmic spans, archives degrade, languages vanish, civilizations fall. The second law ensures that even knowledge must fight for survival against time. Yet there are refugees, data etched in crystal lattices, signals encoded in stable orbits, monuments built to endure. Some information may persist, but only with effort against the grain. The ultimate irony is that even black holes once thought eternal will eventually evaporate through Hawking radiation. Over unimaginable timescales, they will leak away, shrinking until they vanish in bursts of radiation. What remains is a thin sea of photons and particles spread almost uniformly, carrying little structure. In such a universe, complexity will be memory rather than reality. For us, contemplating this fate is not despair, but perspective. It frames our actions in the context of an immense canvas. To know that stars will die and entropy will rise makes our present moment of light and structure more precious. We are living in a rare era when galaxies blaze, when chemistry thrives, when information can be gathered and preserved. Entropy reminds us to value the temporary abundance we enjoy. The heat death scenario is not the only possible ending. Cosmologists have imagined several alternatives depending on the behavior of dark energy and the nature of space-time. In a Big Rip, phantom energy grows so strong that it overcomes not only galaxies and stars but atomic bonds themselves. In the final instance, the universe unravels at every scale, tearing molecules, nuclei and space-time apart. The timeline is speculative, but if dark energy has the right properties, the end could come in tens of billions rather than trillions of years. Another possibility is the Big Crunch. If dark energy weakens or reverses gravity, might eventually halt expansion and drive a collapse. Galaxies would draw together, the night sky brightening as everything crowds inward. Temperatures would rise, stars reigniting in bursts. At the end, the cosmos would condense into a singularity, perhaps to rebound in a new Big Bang. Though current data favour endless acceleration, the crunch remains a theoretical option, a reminder that cosmic destiny is not fixed. There is also the idea of the Big Bounce, where the universe cycles endlessly through expansion and contraction. This model offers escape from the question of origins by suggesting there was no first beginning, only eternal rhythm. Each bounce resets entropy in ways still debated, perhaps through quantum gravity effects. It is speculative, but it hints at a cosmos larger in time than even our imagination. More exotic still is vacuum decay. If the Higgs field that underlies particle masses is metastable, a quantum fluctuation could trigger a bubble of true vacuum. Expanding at nearly the speed of a light, it would rewrite the laws of physics inside obliterating structures without warning. There would be no suffering, only instant annihilation. While calculation suggests the universe is stable for now, the possibility is a stark reminder that even fundamental laws may not be immutable. Each scenario, though grim, serves a purpose. They sharpen our models, motivate observations, and remind us that cosmic evolution is not a closed book. The universe has endings as diverse as its beginnings. Our task is to narrow the possibilities with data to understand not only where we came from, but where we are going. The distant future of a heat-death universe is almost incomprehensible in scale. After stars and black holes fade, the cosmos enters the so-called degenerate era. Planets drift, orphaned moons wander, stellar remnants cool. Collisions become rare, energy exchanges slower. Over quadrillions of years, protons themselves may decay, reducing matter to radiation. If protons are stable, structures linger longer, but entropy still wins. During this time, galaxies dissolve. Without new stars, their shapes blur into collections of faint embers. Black holes dominate, swallowing what remains only to evaporate in turn. When the last one goes, the universe transitions into the dark era, populated only by low energy. Photons, neutrinos, and perhaps exotic relics like dark matter particles. Temperatures approach absolute zero, not in any finite place but across the whole. Yet even in this bleak forecast, some have speculated about pockets of activity. Quantum fluctuations could occasionally create particles. Tunneling events might spawn new universes. Statistical accidents in infinite time could give rise to brief bursts of order, the so-called Boltzmann brains, conscious observers, flickering into existence in a sea of chaos. These are more curiosities than likely realities, but they demonstrate the richness of thought that entropy provokes. For civilizations contemplating such futures, the challenge is endurance. Can information be preserved against entropy's tide? Can energy be harnessed from dwindling gradients? Ideas include Dyson spheres around red dwarfs, hibernation strategies, where societies slow their metabolism, and black hole mining, where Hawking radiation is tapped as power. These are not engineering plans, but thought experiments testing the limits of survival under universal decline. The degenerate and dark eras may never be witnessed by life, but they remain essential to our narrative. They remind us that time is not endless in opportunity. The golden ages of starlight and galaxies are brief. We exist at one of those ages, and to recognise its impermanence is to deepen our appreciation. The silence of a heat-death universe contrasts with the violence of other scenarios. In a big rip, the final centuries would be apocalyptic. Galaxies torn apart, stars shredded, planets ripped from orbits. As the rip approached, even molecules would feel the strain until atoms disintegrated and nuclei flew apart. The universe would end not in quiet fading, but in catastrophic climax. In a big crunch, the reverse drama unfolds. Skies brighten as galaxies converge, collisions multiplying. Temperatures rise as compression reignites dormant stars. Radiation floods the cosmos. Near the end, the night would blaze with intensity, every particle colliding in a final inferno. For any civilization then alive, the view would be both terrifying and sublime. The cosmos consuming itself in a grand finale. Vacuum decay would be more subtle. No warning, no spectacle. A bubble of true vacuum forms somewhere, racing outward at light speed. To those inside, existence ceases instantly. From the outside, there is no chance to see it coming. It is the most merciful and most ruthless of endings. Merciful because it erases pain, ruthless because it erases everything. All these scenarios dramatize the stakes of cosmic evolution. They remind us that the universe is not a stable stage, but an evolving actor. It was born, it changes, and it will die in fire, in freeze, or in something stranger still. To study these endings is not morbidity, but honesty. It is to look reality full in the face, to accept that impermanence applies not only to stars and galaxies, but to space-time itself. The role of science in confronting these endings is not to guarantee survival, but to offer clarity. Knowing the likely futures helps us situate our present. It transforms the night sky from mere decoration into a narrative on chapter among many. Stars are born, they live, they die. Galaxies assemble, merge, dissolve. Universes themselves may cycle or fade. Each step is comprehensible through the same laws that govern an apple falling or an electron jumping between levels. This continuity is consoling. It tells us we are not out of place in the cosmos, but integral. Our atoms were forged in supernovae, our planet shaped by accretion, our species by evolution, our science by curiosity. To project forward is simply to follow the same arc. The end does not diminish the middle, it contextualizes it. Science also arms us with legacy. The data we gather now may outlast our species. Archives left on the moon, Mars, or interstellar probes could carry the story beyond us. Civilizations we never meet could learn from our records, extending continuity, even as entropy gnaws at order. In this way, knowledge itself becomes an act of defiance, a way of pushing back against inevitability. To speak of heat death or rips or crunches is not to extinguish meaning. It is to root meaning in reality. We find significance not in escaping endings, but in understanding them. The universe is vast and ancient, but it is also temporary. That very temporariness sharpens our wonder. Human understanding of the cosmos is remarkable, but it is not boundless. Every discovery reveals both clarity and limitation. Telescopes extend vision, but only to horizons permitted by light. Detectors capture waves, but only in specific frequency ranges. Mathematics models dynamics, but only with assumptions we cannot always verify. The universe is both accessible and veiled. To explore its limits is to explore our own. One such limit is practical. The age of the universe is finite, so the observable volume is finite. No matter how powerful our telescopes, there is a horizon beyond which light has not had time to arrive. We cannot see farther because farther does not yet exist for us in terms of information. This cosmic light horizon is not a technological barrier, but a physical one imposed by space-time itself. Another limit is theoretical. We cannot run controlled experiments on the whole cosmos. Instead, we observe what the universe presents and infer backwards. This method is powerful but indirect. Models must be tested against relics. The microwave background, the distribution of galaxies, the abundance of elements. Each provides constraints, but interpretation is never unique. Multiple theories can explain the same data until precision rules some out. The deepest limit may be cognitive. Our brains evolved to navigate Earth, to hunt, to build, to socialize. They did not evolve to imagine 11-dimensional strings or quantum fields. Yet through abstraction, symbolism and mathematics, we stretch intuition. Still, there may be phenomena forever counterintuitive truths that no metaphor captures. Recognizing this does not paralyze science. It humbles and motivates it. We approach these limits not with despair, but with method. By sharpening measurement, by refining models, by training minds, we push back boundaries. But we also accept that some boundaries may remain horizons not of light, but of comprehension. To live at the edge of knowledge is not defeat, it is definition. It is what makes curiosity meaningful. Mathematics is our greatest tool for breaching the boundaries of comprehension. Equations allow us to step beyond intuition, to describe phenomena we cannot visualize. Maxwell's equations unified electricity and magnetism long before wireless communication existed. Einstein's field equations predicted gravitational waves a century before detectors confirmed them. Schrödinger's equation describes quantum behavior that defies common sense, yet underlies every transistor. But mathematics has its own limitations. Gödel's incompleteness theorem proved that any sufficiently complex system of mathematics contains true statements that cannot be proven within it. This is not a flaw of calculation, but a property of logic itself. If mathematics is the language of the universe, then even the language has edges where silence reigns. For cosmology, this suggests that some truths may be real yet forever beyond formal proof. Another challenge is that mathematics can generate endless possibilities far more than reality embodies. String theory is an example. Its equations admit a landscape of solutions, each corresponding to a possible universe with different constants, which if any matches our own is unclear. The richness of mathematics outruns the finiteness of observation, leaving us with ambiguity. Despite this, mathematics remains indispensable. It is not just a tool, but a compass pointing where to look. The success of equations in predicting unseen phenomena is uncanny, leading some to argue that the universe is itself a mathematical structure. Whether or not that is literally true, the fact that math works so well is itself a mystery worth pondering. In the end, mathematics is both ladder and horizon. It elevates us beyond sense, yet it reminds us of limits. To embrace both roles is to wield it wisely. Physics also faces boundaries set by energy. To probe smaller scales, we need higher energies. Particle accelerators like the Large Hadron Collider smash protons together at near light speeds, recreating conditions fractions of a second after the Big Bang. But even it cannot reach the Planck scale, where quantum mechanics and gravity intertwine. That scale lies 16 orders of magnitude higher than our best machines can achieve. Unless new methods appear, the Planck regime may remain theory without test. Cosmic rays offer glimpses carrying energies far beyond our colliders, but they arrive randomly and without control. Neutrinos and gravitational waves give new windows, but they too face sensitivity limits. Each messenger extends reach, yet each eventually falters. Nature sets thresholds we may never cross. Another barrier is time. Processes like proton decay, black hole evaporation, or cosmic acceleration unfold over spans billions to trillions of years. We cannot run experiments on those timescales. Instead, we extrapolate from theory and indirect evidence. This works remarkably well, but it always leaves room for uncertainty. We are prisoners of our brief lifespans, peering at eternity through keyholes. Yet even here, ingenuity thrives. By building detectors that watch for rare events over decades, by coordinating instruments across continents, by simulating conditions in supercomputers, we stretch our reach. We may not touch the Planck scale, but we can test the edges of models that live there. We may not witness black hole evaporation, but we can study its imprint in analog systems. Science is not about removing limits, but about playing near them skillfully. Another kind of limit is philosophical. Science thrives on falsifiability, the ability to test and reject, but some cosmological ideas resist this. Eternal inflation, multiverses, hidden dimensions, each is mathematically motivated. Each may be true, but direct tests are elusive. The risk is drifting into metaphysics where explanations multiply without constraint. The safeguard is rigor, requiring that even bold ideas make at least indirect falsifiable predictions. History shows this discipline pays off. Black holes once considered metaphysical are now imaged. Atoms once speculative are now routine. Even dark energy discovered by accident became testable through multiple channels. The lesson is not to shun speculation, but to tether it to evidence whenever possible. There are also ethical dimensions. As instruments grow larger and costlier, society must decide how much to invest in questions that may never yield immediate utility. Some argue resources should be spent on earthly problems. Others reply that understanding the cosmos enriches humanity as deeply as art or philosophy. Balancing these views is part of science's future. Finally, there is the existential boundary. Even if science answers every question, it cannot dictate meaning. Knowing the universe will die does not tell us how to live. Understanding quantum mechanics does not explain love or justice. Science frames context but not purpose. This doesn't diminish its power, it clarifies its role. Despite limits, the pursuit itself is transformative. The fact that creatures on a small planet can measure the age of the cosmos, map its structure, and speculate about its fate is astonishing. Each telescope is a prosthetic eye extending beyond biology. Each equation is a prosthetic thought extending beyond instinct. Science magnifies humanity, stretching our reach far beyond our scale. This pursuit also unites. Astronomers in many nations collaborate on surveys. Engineers and physicists join across cultures to build detectors. Data are shared, analyses, cross-checked results, debated openly. The cosmos belongs to no one and to everyone. To study it is to participate in a shared human project, a cathedral of knowledge built stone by stone. The resilience of this project ensures continuity. Even as questions shift, even as horizons close, the method endures. Measure, compare, revise. That method carried us from myths of static heavens to models of dynamic evolution. It carried us from ignorance of galaxies to catalogues of billions. It will carry us farther still, even if not to final answers. At the edge of comprehension, humility and wonder converge. We may not know everything, but we know enough to recognize beauty and coherence. We know enough to keep asking. That persistence is itself a form of victory. The universe may end, but the act of seeking to understand it is timeless. When astronomers look ahead, they imagine the ultimate observatories, the last generation of instruments humanity might ever build. Among the most ambitious concepts is the idea of interferometry on interplanetary scales. By placing telescopes on separate spacecraft orbiting the Sun and linking their signals, engineers could create a virtual telescope the size of an entire solar system. The resolution would be so fine that individual stars in distant galaxies could be resolved, exoplanet surfaces could be mapped, and even faint structures in the cosmic web could be imaged directly. Another frontier is neutrino astronomy. These particles pass unhindered through ordinary matter, carrying information from the cores of supernovae, the centers of galaxies, and perhaps even from the first moments after the Big Bang. Future detectors far larger than today's ice and water arrays could span cubic kilometers of crystal or liquid scintillator buried deep underground or under ice sheets. With enough sensitivity, relic neutrinos from the early universe, survivors from the first second, might finally be captured, unlocking a new chapter of cosmic history. X-ray and gamma-ray observatories will also grow more powerful. Instead of single satellites, fleets of coordinated detectors could measure bursts across the sky, triangulating with extreme precision. Such arrays would provide real-time warnings of supernovae or neutron star mergers, while also mapping the violent regions around black holes. Combined with gravitational wave networks, they would ensure that no event of high-energy astrophysics escapes unnoticed. These ultimate observatories may never all be realized, but their blueprints demonstrate what is physically possible. They show how far curiosity can be pushed with engineering, how much more detail can be extracted from the universe before expansion hides it away. They represent not philosophy but ambition rooted in technology, and the desire to capture as much information as physics allows. Knowledge, however, is not just about discovery but also about survival. Data must endure if it is to be useful to civilizations beyond our own. Current efforts to preserve information include lunar archives, digital vaults in Antarctica, and spacecraft carrying golden records. Yet these are modest compared to what could be done. Truly, long-term preservation requires strategies that withstand cosmic timescales. One idea is to etch data onto stable materials such as sapphire or tungsten, resistant to erosion for millions of years. Another is to distribute copies widely on asteroids, moons, and interstellar probes so that no single catastrophe erases everything. A third approach is redundancy across media. Digital for convenience, analog for resilience, symbolic for interpretability, Future archives might also be encoded into biological systems storing information in DNA sequences that can be replicated naturally. Though fragile DNA has been found intact after hundreds of thousands of years, and synthetic biology could extend its durability further. Combined with planetary vaults, this could create overlapping layers of memory, some technological, some organic. The goal is to ensure that future intelligences, whether human descendants or others, inherit a record of what we learned. Cosmology is uniquely time-sensitive. The evidence for the Big Bang, for cosmic acceleration, for the web of galaxies will not always be visible. Archives carry not only our story, but the universe's story written during the brief window when it could be read. Beyond physical archives, communication strategies matter. Radio leakage from Earth has already been travelling for about a century, a faint, expanding bubble of signals. More deliberate transmissions, beamed with power and encoded carefully, could persist far longer, announcing our presence and sharing knowledge across light years. Directed signals toward nearby stars could include scientific data, universal constants, or maps of cosmic history. Another possibility is to exploit astrophysical carriers. Neutrinos, nearly impossible to block, could be used for interstellar beacons. Gravitational waves, though challenging to produce artificially, might one day carry signatures across the cosmos. Even encoded modulations of pulsars, the universe's natural lighthouses, have been proposed as information channels. These strategies are speculative but grounded in physics. They demonstrate that communication is not limited to one medium. The more varied the messengers, the better the chances that something survives the erosion of time and distance. Preserving knowledge is not an afterthought, but an extension of observation. If future skies grow empty archives and signals become the only evidence that galaxies once filled the night, the act of transmitting is itself a scientific experiment. Will the cosmos respond, or will silence be the only reply? Preparing for the universe's silence also means maximizing what we know now. Surveys that map billions of galaxies, detectors that capture faint signals, and simulations that model structure formation are all part of a global archive. The challenge is not just to collect, but to integrate. Cross-linking data across wavelengths and messengers creates coherence. Each piece is valuable, but together they tell a story no single dataset can provide. This integration requires computation at unprecedented scales. Simulations now track trillions of particles reproducing the cosmic web from inflation to present. Machine learning helps identify patterns in noisy signals. Distributed networks process floods of observations in real time. These tools turn raw data into knowledge into understanding, and understanding into legacy. The closer we come to cosmic limits, the more vital this integration becomes. We may not extend the horizon, but we can maximize clarity within it. The universe is generous in offering information now. Our duty is to capture it fully, preserve it carefully, and interpret it honestly. The final chapters of cosmology will not be written in despair, but in detail. Whether the universe ends in heat, death rip crunch, or bounce, the record we compile now will outlast immediate observation. Our telescopes may one day fall silent, but their data can remain. Our detectors may no longer hear, but their results can be stored. The story of the cosmos is temporary in evidence, but permanent in principle, as long as someone remembers. What matters is not just survival, but continuity. Each generation builds upon the last, refining instruments, tightening models, pushing boundaries. The chain may break someday, but until then it lengthens, linking minds across centuries. The stars themselves are transient, yet the knowledge of stars may last longer than stars. Cosmology, then, is both science and heritage. It is our attempt to capture not only how the universe works, but how it changes, how it ages, and how it will end. The data are the script, the theories are the interpretation, and the archives are the stage upon which future audiences may still witness the performance, even if the actors have long exited. The universe is vast, ancient, and still full of unanswered questions. From the first sparks of inflation to the fading glow of distant galaxies, from the roar of black hole mergers to the silence of future isolation, we have traced its story as best we can. Our instruments extend our vision, our mathematics sharpens our models, and our archives preserve the fleeting signals that reach us across billions of years. Yet every answer leads to deeper mysteries. Dark matter remains unseen. Dark energy remains unexplained. The fate of the cosmos remains uncertain. But this is not defeat, it is the invitation that science offers, to keep asking, to keep building, to keep listening. We live in a privileged moment. The night sky still blazes with galaxies, the cosmic background still whispers its origin, and new messengers still arrive. Never again will the universe be so generous with information. We are its witnesses, its archivists, and its storytellers. And so the story does not end here. It continues every time we lift a telescope, refine an equation, or preserve a record. The cosmos is not only out there, it is within us, in our atoms, in our curiosity, in our drive to understand. Thank you for joining this journey through time and space. Stay with me because the universe always has another story to tell.